Okay, hello everyone. My name is Tommy Kahneman. I am the Executive Director of the SU2 Foundation. And on behalf of the other members of the board, Juan Alonso, Eran Arad, Tim Albring, and Ruben Sanchez, I want to welcome you to what we're calling the first annual SU2 conference. And I want to give you all a warm welcome and let you know that just because we're doing this virtually does not mean it's going to slow us down at all. And in fact, we have the most content of any annual meeting we've had. And so for the next 30 minutes or so, I'm going to be your guide. My goal here in this talk is just to welcome everyone, give you an overview, get everybody excited, tease some of the talks you're going to see in the next 3 days, and get everybody fired up for a good conference. So just on a personal note, you know, this talk is kind of a highlight of mine each year.
My goal here in this talk is just to welcome everyone, give you an overview, get everybody.
And there's a little bit of feedback. Okay, sorry about that. So this is a personal highlight of mine each year. I really look forward to giving this talk, and I hope you all enjoy. So we've been fortunate in this community over the past few years to have annual meetings at some really great locations. So in 2016, we had a meeting together at TU Delft, followed by a meeting at Stanford in 2017. After that, we met together in the UK at Strathclyde. And just last year, we had the opportunity to get a wonderful venue in Italy and be together. And these meetings are in the past, they've been all about getting the developers together primarily to talk about code issues, get together as a community, understand what we can work on, and see each other's work. And with this meeting the last year, in 2019, we have been witnessing that the sizes of the meetings are growing. And we really wanted to open it up and see just what all the other folks in the world are doing with the software. So beyond just developers, which is what we've called this meeting prior to now, we wanted to make it more about users and the entire community. And so instead of this year calling it the 5th annual SU2 developers meeting, we've decided to call it the first annual SU2 conference. And we intend to keep it that way going forward. And the idea really is to, as I said, open this up and show a lot more of what users and other folks in the community are doing, and invite more folks to come give talks. And I think our hunch was a good one. So just this morning, I saw we sent an email reminder for this conference to over 400 people. I think there's some hunger to sort of join and share results that people have by using the code and share what they're doing in the community. So I'm just very excited that we can do that, and I'm glad you all can join and be here. So the typical thing we show at the beginning, just to make sure everybody's on the same page about what the motivation of this project is the following. So I like to use this slide. This is a picture of the website from right around when the project started in 2012. And you can't read it, but I'm gonna blow up the quote that's there on the front page, and I'll let you read it. I've highlighted a few things in there that really remain core to the project and are still ringing true today. So in particular, the project is about multiphysics analysis and design optimization. It is freely available as open source. And we really do mean it when we say we're trying to involve everyone in the creation and development. And so this still rings true today. And just for those who perhaps are uninitiated, we also like to just overview what the key technology features are of the SU2 package. So it is a software package for multiphysics analysis and design on unstructured meshes. And we've always believed in the importance of providing gradient information through adjoints. And that's been baked in since the start of the project. It is an open source project. This is one of the other most important aspects of the project. And it's released under the LGPL 2.1 license, and that's freely available on GitHub. The source code has been designed to be reusable, readable, and portable. And so we really do view this as a research platform for the community to use in everything from CFD to multiphysics,
Yeah,
adjoint
I'll send you
methods,
the YouTube link. I'll send
high
you.
performance computing, and more. And we also are, something that's important for us is making sure we can take what is an open source code and is reusable and readable, but also make sure it is ready for industrial type cases. And therefore, we always focus on making sure that the performance is adequate and it is HPC ready so that you can take it and run it on larger resources. So let's do some review of some key milestones in the project. And so this is a timeline from the start of the project in 2012 when we first released version 1.0 up through today, this meeting. And you'll see a number of highlights there on the timeline, in particular those developers meetings that I mentioned before, but also in the little teardrops you're seeing when we released each of the major releases of the software, so versions 1 through 6. And I want to say a little more about some background in the project in terms of numbers. So the first thing I want to put up is a screenshot here of the Google Analytics from our SU2code.github.io project page. And so you're seeing this colored by access to that website, web hits there. And rather than getting lost in the details, I think all that's important here to say is that you can just tell by the coverage that we are reaching a wide audience here across the world, something that we're very proud of. And if we talk about some more specific numbers, we now have over 2,000 people registered on our email list. We have over 6,000 repository visits in a 2-week period. So each 2 weeks, 6,000 folks click around on our GitHub repository. We have over 1,000 repository clones every 2 weeks. And since we've started doing releases on GitHub, those binaries, the assets that are put up there, have been downloaded over 10,000 times. Now, if we look at the email list, so the folks that have voluntarily offered to categorize themselves when they sign up, we see the pie chart here that shows kind of how they would classify their usage of the code. So whether they're a user, developer, academic, or industry. Note that here in this figure, actually people can pick multiple. So I think I, for instance, picked all 4. But it gives you some idea of how people that are using the code would classify themselves. We also have this plot provided by HubSpot, which shows, it takes information from internal databases of email addresses and kind of categorizes it by industry. And you can see here that we have a very strong showing from higher education and research of the users of the software. Now, the other thing I wanted to talk about, not just the project numbers, but development numbers and some specifics about how we do development and what that looks like. And so this plot is taken from GitHub. This is from the time we first posted the software on GitHub up till what I've done is cut it off at last year's developers meeting, so in 2019. And you can see that since we put it up 2013 or so, you see we've had sort of a steady growth. And this is our commits to the repository. So on the left axis, you're seeing how many commits. On the bottom is time, of course. So these are, basically just think of this as people's contributions to the code as they're submitting their software contributions. And so what I wanted to highlight is that from last year's meeting until now, we've seen an explosive growth in activity. And we have a lot of folks getting involved on GitHub, a lot of action in the issues and pull requests, and a lot of code being submitted. And we can get more specific about that. So as of version 7.0.5, I just collected these statistics over the weekend. We're at around 163,000 lines of C and C++ code. Just in this last year, that period that I just highlighted, we have processed 154 pull requests. And for those who are not as familiar with GitHub, this basically just means 154 contributions from the open source community that we've merged into our main line of the code. We have at all times while we're sleeping, and probably even right now, a whole suite of continuous regression and unit tests. And we have 378 of those just running all the time, protecting our software. We have over 200 active branches in the repository. So these are our feature branches or bug fixes that folks are hacking around on right now in the main repository. In the past year, a little over a year since the previous major release, version 6.2.0, we've made over 4,000 commits to the master branch, so our main line. And we have almost 500 active forks on GitHub. And this is basically a proxy for developers in a sense. So these are folks that have made a copy of the software into their own GitHub account for purposes of modifying it, making changes, and often cases actually submitting that code back to us for inclusion in the repository. Now, a little more specifics on the code in terms of lines and how things have been progressing. So what I'm showing on the left is a plot of the lines of code by release. So on the left axis, you have just the lines and thousands. And at the bottom, it's a little small, so forgive me, but the numbers there at a 90-degree angle are the release numbers of the code. So, with time, we're increasing here all the way up until what we call the develop branch. So basically the most recent version of the software that hasn't been released yet. And there are a couple things to highlight. For quite some time, the number of lines of code were pretty much static. We were hovering around 100,000. This, I should say, is excluding any of the code that's found in the externals directory. So this is just SU2 software, ourselves, our own code. I also want to highlight there are a few big jumps here. So versions 5, 6, 6.2. The time in between these jumps is actually quite large. So maybe it's a little unfair. It looks like we're taking a couple very large hops. There's actually quite a bit of time there. But the most important thing I want to highlight is that since version 7, so right around here, if you can see my cursor, since version 7, the community's really had a consolidated effort to sort of put in, as we put in more capability in the code, actually try to reduce the lines of code, be a little more lean and better organized. And you're starting to see that pay off with this downward slope of our lines of code. And another very interesting thing has happened. So if we look at now on the right, the number of files in the project by release, so same idea, now it's number of files, but by release number. Since version 7, you're also seeing a large increase in the number of files. And the reason for that is we wanted to break down the files to make them a little more manageable and make sure that we're sort of putting, one class per file, et cetera, following some other practices. And what that results in is a major drop in now what I'm plotting the lines per C++ file. So over time, that had been creeping up to around 1,100. And just within the last few releases, you can see that just plummeting down to about 300, 350 lines of code per C++ file. And this just lets us be a lot more organized as a team. It makes it easier for folks to, in the open source community, to develop these files, less conflicts, easier to learn, easier to understand, more readable. So we're very excited about this. And I just want to plug that if you're interested in much more detail and depth on how we do development, how we use GitHub, all the open source practices we use, see the talk by Tim on Thursday. He'll go into all these details. Okay, so I like to summarize our impact over the years as a community in the following way, just by orders of magnitude. So I would say we have thousands of users, hundreds of developers, and dozens of institutions that are generating thousands of commits, hundreds of pull requests, and dozens of releases at this point. And this attracts thousands of repository visits, hundreds of repository clones every 2 weeks. And we're outputting thousands of hours of training, hundreds of research papers, and dozens of theses. And really, at the end of the day, this is all for educational and research purposes, and we're still counting. So at this point, I want to use that as a transition to talk about another major milestone that happened last year, which is the forming of the SU2 Foundation. And this is actually in response to what I just talked about. The community is very vibrant. We're generating a lot of content, a lot of code, and we're often asked, how are you going to sustain that effort? So if you'll allow me to use an analogy, and I like to compare the code to a city, and since I'm a little biased, I'll take the one that's closest to me. And in this code city, we always have, shiny new research, which is great and gets a lot of attention. We have things like new interfaces and coupling for multiphysics. We have well-established capabilities, finite volume method, adjoints, etc. But we also have some really critical infrastructure that just needs to be taken care of by the team. And this includes things like I/O and MPI and class structure, etc. And for years, we were asked, a good question, frankly, is how do we sustain our project? How do we keep growing? How do we scale up? Given that, it was sort of a grassroots organic movement to build this project. And so our answer for that as a community over the past couple of years has been to form a legal entity that's a nonprofit. And we call this the SU2 Foundation. And this has been in existence now since last May. It's a nonprofit, non-stock corporation. So that means any funding we bring in is used purely for the mission, which I'll tell you about in a second. And there are no owners. So in fact, the community are the owners, the public are the owners. And we are pursuing 501c3 status in the United States as a charitable organization. We're in the final stages of that. So we hope we can report back on that soon. So what is our mission? So the language here is a little formal. This is directly off of our document that we filed. And it's the following. So our mission is to promote global software development and education to increase the pace of innovation in the engineering sciences for the public benefit of all society. It's kind of a mouthful. And also to provide a neutral forum for community collaboration and offering efficient infrastructure and technical governance. So what that really means is we're an engineering, a scientific and educational nonprofit. And I want to really emphasize the public benefit for all society aspect. I just want to note that we take that very seriously. We do promote diversity and inclusion, and we really want everyone to feel welcome in the SU2 project. We do our best to support each other and make sure it's a community in the truest sense possible. And as you've all found, because you made your way to this meeting, we have information posted on our foundation website. That's at su2foundation.org down here. And we also have an email address, info@su2foundation.org, where you can reach the foundation team. And I'm just showing a splash screen here of what the website looks like. And I would ask, when you have a moment, please go there and sign up for our email list if you haven't yet, so you can keep in touch, hear about our developments and announcements and whatnot. Now, we do have a little bit more news about the foundation. So I wanted today to tell you a little bit about the SU2 Foundation sponsorship program. So advancing this mission that I just explained to you depends on generous support from individuals and organizations around the world. And we need your support to survive. And we use this support to do things like put on events like this, community outreach, organizing more meetings and training and educational events, creating educational materials, proactive maintenance of the software, etc. And so today we're very excited to announce officially the SU2 Foundation sponsorship program. And the idea is we want to recognize our donors at 4 different levels. So we call them pioneer, innovator, investigator, and collaborator. So pioneer being the highest level of recognition. And not only is this a sponsorship program available, so we have a document that's going to be available for release. It is available for release. We'll be posting information soon. We also have a white paper on benefits of involvement with the SU2 community that's coming very soon. And I just want to take a moment to thank the SU2 Foundation External Affairs Committee and the fundraising committee, who have been putting in a ton of time creating material and helping generate the sponsorship program and the white paper and other content for the foundation. Thank you very much for that. Now, the new sponsorship program actually already has some generous sponsors. So I want to take a moment to thank them. First of all, at the pioneer level, the highest level, we owe a very large thank you to Robert Bosch LLC for their support. The funding that we received, the donations from Bosch have really let us, have kept us alive the past year, if we're being honest. So we really do appreciate your support, not only in the forms of donations, but I should say that the folks at Bosch are also putting a ton of work in on scientific contributions, working on the code, and that's apparent because in each of the 3 days of the conference this week, you can actually see a talk by Bosch associates and people affiliated with Bosch. So I'll just point out that Daniel, Toby, and Philip, I would like to say you should all join their talks in the coming days. And I'd be remiss if I didn't also acknowledge a few other organizations that helped us right at the beginning at a critical time when we were just getting started. And that's Delft University, University of Twente, Politecnico di Milano, and the National Institute of Aerospace. So thank you for your generous contributions to the foundation. Okay, now in the last part of this talk, I really want to focus on some technical things and try to get you guys excited about what's coming this week. And I should say before I launch into this that these results obviously are not my own. I've had a lot of material shared by people that are going to be presenting in the next days. And I also should say I wish I could show more. I could only grab a few tidbits. So I apologize to those who maybe are not, their work's not seen here, but thanks to those who have shared some nice images and things. So let's first talk about some development highlights. This is maybe getting a little bit into the nitty gritty, but I want to just demonstrate that explosion of activity that I mentioned before. So inside of GitHub, I mentioned that we have these pull requests, and these are contributions that people make to the community. And I'm just going to call out a bunch here, and those are actually numbered. So you can see I'm going to number the things here. If you're interested, you can go and dig into GitHub and look at that all these changes entail. But here are a few things that developers have been doing for the past year. One is addition of hybrid OpenMP MPI, and that actually spans over a number of pull requests. We have modernization to C++ throughout the code base, which is just ongoing over the last year and a half. In number 853, we had a compilation speed up of roughly 10x. So that helps all the developers. Everybody was very happy after that. We have a new unit testing framework that was released in 850 based off of the Catch2 framework. You'll hear about that. We have a new automated release workflow. We're really leveraging GitHub Actions now to have much wider CI continuous integration coverage on more platforms, including Windows, Mac, Linux. During that time, we've also had many algorithmic improvements, performance optimizations, robustness considerations, resulting in, case dependent, of course, but up to 10x speed up in the code. And there are a bunch of pull requests here you can go take a look at if you're curious. Addition of fully customizable user output. So finally, folks can pick, from the config file exactly what they want to put in the output files, which is a highly requested feature for a long time. We have a new solution verification framework. And of course, there are just too many to include. But I do want to highlight that the ones in blue here will show up in talks during this event. So, if you stay tuned the next 3 days, some of our developers are going to give what we're calling feature talks that go into some of these topics. Okay, and now I want to show just a few teasers of what people are actually doing with the SU2 software now in version 7 and in the community. So the community, has people working on all sorts of applications, doing research in all sorts of areas that include things like topology optimization, multiphysics, including conjugate heat transfer, turbo machinery. You also see things like work on mesh adaptation, pressure-based solvers for wind turbine aerodynamics, and even a nice effort that Giant will speak about on Friday, which is trying to run some simulations in support of the creation of cheap ventilators. And I'll leave it to Giant to talk about that, but you're seeing an animation here of kind of flow through a simple 2D ventilator. Apart from that, we have folks working on high-speed non-equilibrium flows, so things with very complex high-speed non-equilibrium characteristics, like you're seeing this double wedge problem here, very complicated flow physics, or hypersonic vehicles, so space access. You're seeing some Apollo capsule runs here on the right that have been done with SU2. And I would just call out that if you're interested in some of these topics, you should see the talk by Catarina later. We also have folks working on, actually a lot of work on scale resolving flows and also aeroacoustics. So I was given these images by Beckett, so I recommend you stick around for his talk in a little while. And here you're seeing some DES type calculations for tandem cylinders, as well as turbulent jets, including aeroacoustic predictions compared to experiment. And starting to show some very, very promising results in that area. So I recommend you stick around for that. Now, we actually have a couple different solvers that folks are working on in the scale resolving regimes. So on the left, you're seeing a discontinuous Galerkin finite element solver in implicit LES mode. That's the SD7003 airfoil. On the right, you're seeing the NASA hump. And so I just want to say that there's a lot of effort right now being put into sort of not just sort of DES type scale resolving flows, but also LES and wall modeled LES in both the finite element and finite volume versions of the solver. And so I just want to tease this a little bit. This is work that is being done by Eduardo and some other collaborators. He's going to talk about this next, so I think everybody should stay tuned for that. And these are some of the first wall modeled LES runs that are coming out. Very preliminary, but very exciting work. This is the Lagoon landing gear on the left and the NASA juncture flow geometry on the right. And this is, I believe, Y+ on the surface, just so you can see the behavior of the flow on the surface. Okay, so now just to say a word or two about the program and how we want the next few days to go. So we have 25 live talks, and they're featured and lightning formats is what we call it. So the ones that are a little bit longer are about 30 minutes. Those are featured talks, and then the others are lightning talks. And these are all being recorded. They're going to be posted to the web afterwards. And we would like folks, if you have questions, to post them in the GoToWebinar chat. We've reserved about 4 minutes at the end of each session, at each talk, to discuss Q&A, and we'll sort of moderate that. But please do leave questions in the chat window. And there's not only those 25 live talks, but there's also additional contributions on the web. So there are other slide sets and video uploads that people have already given us that we've posted to the website. And you can see the URL here. So please go to the website and check out the other great content that people have loaded, including full 30-minute versions of some of these short lightning talks. And I just want to call out one particular set by Brandon Gleason here that was submitted with some very nice comparisons between CFX and SU2, including not only flow field, but also comparisons with experiment and the two solvers compared head to head, which are very, very nice results. So there's a lot of great content there. I hope you'll take the time to go to the website and give it a look. So this is the agenda for today. And again, this is at the conference website. We'll continue to kind of bring this up and introduce each of the speakers when the time comes. With that, I just would like to leave you with some final thoughts. And I want to say that we do want everybody to get involved. We want you all to join us in this mission for education, research, and innovation. And we really are trying to benefit society, and we want this to be a vibrant community. So here's how you can get involved. First of all, very easy one, please just join our email list. So go to the foundation website and stay connected. You'll get newsletters and updates that way. The next thing is, if you're a user or a developer of the code, please do get involved, get in on the action on GitHub. So, jump on the repository, which you see the link for there. There's just a ton of action happening, a lot of issues, a lot of pull requests, a lot of conversation. There's a lot to be sort of learned and shared on that platform. So please just get involved. Your participation makes the project very, much more vibrant and valuable. And lastly, if you're interested in any of the foundation programs and sponsorship, we do invite you to contact us either personally or we do have the foundation email list there. but please just get in touch so we can discuss, whatever it is, maybe training or sponsorship. So with that, I will stop right on time and we can transition to the next talk. So thank you all for being here again. Really excited for the meeting, and yeah, we look forward to talking to you more. So now we are going to transition to our first talk. So I would ask Eduardo if you can turn on your camera. There you are. And I'd like to give it over to Eduardo Molina, who's a postdoc at Stanford, who's going to talk to us today about scale resolving simulations in SU2. And I think a lot of folks are looking forward to this one, so take it away, Eduardo.
Okay. Thanks for the introduction, Tom. And today I'm going to tell you about a set of new capabilities that we have implemented over the past 2 years to enable scale resolving simulations in SU2. It's well known that runs have some limitations with incipient separations, mixing, transition flows, and shock boundary layer interaction. Therefore, we plan to mitigate these limitations with this new set of capabilities that I will present herein. So here is the outline of my presentation. I will start with the motivation of this work. I will show the development of hybrid runs LES and wall model LES models in SU2. Also, I will show some guidelines of scale resolving simulations, how to set up the code, generate the mesh, choose the numerical methods. And after that, I will jump in the VNV. So I will show the validation for the wall model LES in the turbulent channel flow. And also I will move to a complex geometry test case, which is the lagoon landing gear. And I will conclude this presentation showing the ongoing and future work. So in addition to the run's limitations, there is an increasing pressure for accurate prediction of areas at the edge of the flight envelope earlier in the design process, mainly to increase performance and reduce noise and increase safety. And also, we plan to demonstrate that scale resolving methods can lead to high levels of confidence on design and off design condition. So this figure shows different flow conditions dominated by turbulence where scale resolving simulations can be used to increase the fidelity of the model, of the aerodynamic model. And today we will be focused on landing gear flows. So current numerical methodologies have to be able to cover a wide range of applications, ranging from external aerodynamics to internal flows. The classical approaches are the runs and LES. The runs models relies on the modeling of the entire turbulent spectrum. On the other hand, LES, it's a well-known technique that correctly simulate the spatial temporal dynamics of turbulent flows by decomposing the aerodynamic field into a resolved large scale and a model in small scales of the flow. The main obstacle to use LES in practical industrial flows involve the resolution requirements of the boundary layer in the high number flow regime. Furthermore, it can be argued that the simulation of the dynamics of small scales in attached boundary layer is often not necessary from an engineering point of view. Wide flow separation and free shear flows must be correctly captured. So for that reason, hybrid runs LES and wall model LES were developed to alleviate the resolution constraint of wall resolved LES in the near wall regions, and allowing an LES-like turbulent behavior resolution everywhere else. And also, it's arguably that hybrid runs LES and one model LES are the most promising strategy for making LES more affordable at high Reynolds numbers and in a wide range of complex industrial applications. So scale resolving methods in SU2, the first model that we implemented, it is the non-zonal hybrid runs LES delay detached eddy simulation, so DDES. It was first developed by Philippe Spallert. Also, we added the improved DDES, and recently both approaches that are based on the SCA turbulence model, we will use the new Shirley adapted subgrid scale model. That's it's the most recent model that tends to alleviate a little bit the gray area. And this is how the models behave. You see the runs equations are solved near the boundary layer, and the LES is everywhere. And this transitions between runs and LES is fully automated, so there is no user intervention. And here is how the models behave in the more complex test case. This is the tunnel cylinders and flows, and you see that here on the wall we see high values of the length scale, and you see lower levels on the wake, showing how the models is behaving. So the second model that we implemented is the wall model LES, and for that we choose the basic algebraic wall model, which is based on the law of the wall. And the second model that we implemented and added is the 1D equilibrium wall model of Kawai and Larson. So the main difference between wall model LES and hybrid runs LES is that the LES extends all the way to the wall, and the wall model LES uses separates the couple wall power grid to the calculation. So this is how the wall model works. We have exchange locations, which are the blue dots, and those informations are extracted from the LES simulations, and it couple in the wall model, and we solve the shear stress and the heat flux if necessary, and then we apply this back on the red points of the wall as weak boundary conditions. And the exchange locations, the search are fully automated, and also the calculation of the interpolation points. So the user just need to add the exchange location height, and the code take care of everything. So here I would like to talk about some guidelines for scale resolving simulations. If one would like to start using the DDES, we suggest starting with this enhanced DDES using the Shirley adapted STS model, and the user just need to add the following three options on the config file. On the other hand, if one would like to start with the wall model LES simulation, we suggest starting with the logarithmic wall model coupled with the Freeman STS subgrid scale. So the user needs to add the following options, and also here needs to specify the marker for which you want the one would like to apply the wall model, and also the exchange location. If one would like to export the wall model variables, such as the heat flux and the shear stress, you need to add the following option to the volume output. And talking about mesh generation, this is just a guideline for the user to start creating their own meshes. So we suggest that the maximum spacing should be on the surface, should be between 0.5 to 1%, of the reference length. The reference length here can be the ones that one used to calculate the Reynolds number. On the other hand, on the wake region, we suggest a maximum spacing of 1% to 2%. Regarding the first point of the wall, we suggest for the DDES y plus of near 1, and for the wall model LES and y plus between 50 and 100, and choose the exchange location to be between the third and fifth node. Regarding spatial discretization, one needs to select a low dissipation convective scheme. Can be the modified JST or the simple low dissipation OSMO that are good candidates. And the user should add those following settings to the config file. Regarding the time discretization, the user needs to select a maximum time step of 1% of the convective time step. Turn on dual time stepping with 10 linear iterations and expect a density residual reduction between 2 or 3 orders. And also, one thing that was added recently in version 7 is this new robust controller CFL adaptation, and this I suggest to turn on also, and this will help a lot on the convergence on the dual time stepping. So these are the general guidelines. So now let's jump to some previous examples that I would like to show some validation test cases that we run over the past 3 years using the DDES implementations in SU2. So the first one that I would like to show is the flow around tandem cylinders, which is a prototype of a landing gear flow. And the second is the round jet noise for aeroacoustics. And the third one is the transonic wing buffet that we did for the aeroelastic prediction workshop. And the fourth test case is the vortex breakdown of the delta wing. And last but not least is our participation on the automotive prediction workshop. So we are also exploring flow around automotive configurations. Now that we have confidence on the DDES solver, we'd like to verify and validate our new wall model LES code. So for that, we select the turbulent channel flow case at a friction number of 5200 with the algebraic wall model coupled with the Riemann SGS. So this is a basic channel flow with periodic boundary conditions on the X and Z directions, driven by a constant body force. And the computational domain is 2 pi in the streamwise, 2 boundary layer height on the wall normal, and P on the spanwise. And the mesh size is 96 by 48 by 48 with a target Y plus of 100. And here on the figure, you can see the effect of the exchange location. So the red curve, we are extracting information on the first point of the wall. On the green, we are extracting on the third point, and the yellow on the fourth, and on the blue on the fifth point of the wall. And you can see that there is a good agreement with the DNS in the outer layer if we extracted informations between the fourth and the fifth points. So this is the main takeaway here, is that the user, our recommendation is to place the exchange location beyond the third cell. So using all this structure that we implemented, we decided to test our model in a more complex industrial-like test case. So for that, we selected the Lagoon nose landing gear, which is a simplified landing gear. It's a joint project by Airbus and Molina. And the objective here is to build an aerodynamic acoustic experimental database on a two-wheel simplified landing gear for flow and noise prediction. And this experimental data, it's very complete. There is pressure taps, collides for pressure transducer, and hot wire PIV, and LDV measurements. And regarding the flow conditions, it's a nominal Mach number of 0.23, and the Reynolds number based on the wheel, it's around 1.2 million. Now I would like to show you some the mesh details of this geometry. So the mesh was generated using the latest pointwise voxel feature. And we follow the guidelines that I previously mentioned. But here we also added a constant size region on the wake with 2.5 diameters downstream of the wheels to better capture the turbulent structures. Also, this grid follows the AMR Cartesian type grids with 6 levels of refinement. So each jump in the refinement, the grid is coursing twice in each direction. And this proved to be a very fast turnaround. You can generate this grid in your laptop, and it's almost fully automated. And the first point here of the wall is 0.2% of the wheel diameter, and the exchange location is between the fourth and fifth element. So here is the computational details. So we run these test cases using our new wall model LES code and also using the DDES code. The main difference between both approaches relies on the same grid. We just changing the first grid of the wall to be the target Y plus. So for the DDES, it's a Y plus of more or less 1. The wall model LES, we turn to be like for 50 to 100. This turned to be a difference on the mesh size, of course. The wall model LES has 27 million, and the DDES has 34 million. And other than that, the spatial discretization is the same. We use the JST modified one with implicit dwell time stepping. And this leads to a difference in the wall time hours. Here that we can see, it's 29,000 hours for the wall model LES, which means that if you allocated 1,000 cores, you can have the results this in 29 hours. So this is a very good and a fast turnaround for the results. And for the DDES, because the grid is bigger and we are solving one equation more, we have it's 1.5 times lower than wall model LES, but it's still a manageable time. So here I would like to present the instantaneous flows. We have on the right the wall model LES, on the left the DDES. So the first in the movie, is the surface Y plus field. Color in the DDES and wall model LES. The first thing that can really catch your eye is the difference and richness of the structures in the wall model LES compared with the DDES. One may claim that this is the difference because on the DDES we are solving the runs equations on the boundary layer. That's why the dynamics is not so rich. Regarding the wake, where both approaches tends to return an LES-like solutions, the wake are the dynamics are very similar. So even that the scales are a little bit similar, but we have some main difference here: a delay formation of the vortices behind the structure that we don't see this in the WMLES simulations, but in general, the pattern is very similar. Now, regarding the surface pressure, this is the time average results. We have the mean and RMS pressure on the wheel perimeter, and we just see here on the surface pressure the difference between the effect of the boundary layer tripping that we are not tripping in the WMLES solution. So we have this difference that reflects also in the RMS pressure. We have the peaks are slightly shifting, meaning that the point of separations are different. And we are still investigating this difference in the RMS levels between DDES and WMLES on the attached part of the flow. And on the right here is the PSD comparison between two regions on the wheel, the downstream of the wheel here on the leading edge where the flow is separated. The first here on the top, the point is near the separation point, so we see that a good agreement between WMLES and DDES, except here for the peak on the DDES, this light peak. And on the second figure, exactly where it's fully turbulent and separated, we see a very good comparison also. Now the velocity profiles on the wake. The experimentals also include mean and RMS data generated by the laser Doppler velocimeter. So we have the WMLES and DDES, the DDES in the blue line, the WMLES on the red line. Both the streamlines and normal components of the velocity are in good agreement. Even the RMS, the fluctuations on the wake, they are well captured. And here, where there is the profile, which is near the struct and the wheel, we see the effect of the structure here is well captured. Even the RMS values are in good agreement. So in general, both WMLES and DDES results shows good agreement with the experimental data here the wheel. So here I will like to show a general overall comparison using the PIV data from the experimental. So this is a plane on the wake of the landing gear. So the first is the RMS velocity in the streamwise direction and the spunwise, and the RMS velocity from the experimental data. You can see that the WMLES and DDES, the fluctuations are on the same order. The pattern is very similar to the experimental data, and we can see that there is a very good qualitative agreement between simulation and experimental data. Lastly, I would like to conclude showing some very brief far-field acoustics for the WMLES. So the PSDs that I show here for the experimental data, they are corrected by background noise, atmospheric absorption, and the effects of the wind tunnel. And I choose this microphone, which is on a distance of 20 wheel diameters and in 120 degrees of the landing gear in the flyover position. It's flying over the landing gear. And we see a very good agreement with the experimental data up to 1.5 kilohertz. And in the bottom figure is the overall sound pressure level, which is integrated all the microphones and the frequency range. And I compare with the experimental data, and we can see that a slightly difference between 1 dB to 1.5 dB with experimental data. And so now we move to the conclusions and future work. I would like to say that we are very happy that now we have DDES and wall model LES scheme resolving simulations are available now in SU2, and I really encourage you guys to download the codes and try on your test cases and do the feedback for us. It will be really appreciated. You can find the source code on our GitHub branch. And also, apart from that, we have a complete set of validation test cases that include not also the channel flow, but also the duct and also hump, and also the lagoon that I previously showed. And our future work, which will be merge this branch to the developer for a future release. And also, I would like to show you some ongoing simulations of the NASA juncture flow, as are the wall model LES simulations that we are currently performing. And I will leave the acknowledgements here, and I'm happy to answer some questions.
Okay, thanks, Eduardo. If folks have any questions, you can please, as a reminder, put them down in the GoToWebinar chat window. So I see there is one. We have a minute for questions, so let's answer that. I'll read it out loud. Is it possible to use the DDES or wall model LES with the DG scheme in SU2?
Only the wall model LES, not the DDES.
Okay, so wall model LES is available in the DG,
Yeah,
but not the DDES.
But not.
And Eduardo, is there any, have you guys been working on RANs at all in the context of the DG solver, or is it still just Navier-Stokes?
It's just Navier-Stokes.
Okay.
We are.
Another question, Eduardo, could you talk more about transonic buffet simulations?
Oh, yes, I can return there. So these transonic buffet simulations we perform using the DDES for the aeroelastic prediction workshop, and for that we use the simple load dissipation scheme, the SLO2 coupled with a shock detector. Oh, they are all already available in SU2, so people can reach me and I can explain the config file if one would like to do, but it's all available. All the tools are available.
Okay. Wow. Now folks are adding a lot of questions. So maybe a couple quick ones. A, is there an article available yet to read? And B, is DDES wall model LES ready for supersonic internal flow?
If one couples with answer for the question A, we don't have yet a paper. We are planning to submit a paper for the wall model LES. For the DDES, there are some references on the examples, and so one can follow. Regarding for the wall model LES with supersonic internal flows, if one's again choose the correct numerical scheme, convective scheme, I don't see any reason why it shouldn't work.
Okay. Maybe a last question, and then we'll prepare to transition presenters. So one final one. The wall model gives you the wall shear stress. How is that then enforced at the boundary? A Neumann BC on the wall with parallel velocity components?
Exactly. So we apply this information as a weak boundary condition. So we take the shear stresses and we apply this on the viscous flux of the wall. It's a Neumann boundary condition, so you have a velocity on the wall.
Okay, fantastic.
Velocity,
Eduardo,
right?
there. Sorry, Juan, go ahead.
I was saying there's a slip velocity at the wall, and the shear stress and the heat flux are imposed from the wall model.
Yeah. Okay, so it's time to transition. So there are a few more questions. Eduardo, if you have a minute after you're offline, if you want to take a look and you can respond privately, or maybe folks can contact you, please do that.
I don't see the questions here. Could you please?
Okay. Yeah, let's take it offline. I'll send you something and you can take a look. Or folks, maybe they can just contact you directly. So, great. So thanks again, Eduardo. At this point, we're going to transition to the next speaker. So Pedro Gomes is going to speak about hybrid parallelization of SU2, so OpenMP plus MPI. And Pedro, I'm going to unmute you. Looks like you already are. Can you hear us, Pedro?
Yeah, I can hear you, Tom. Can you hear me?
Yes, sounds great. Okay, take it away.
Good.
It's all yours.
I cannot take it away, so someone will have to flip through the slides for me.
Yes, we got it. You say next. Go ahead.
Yeah, I'll say next and take that as next, please. Okay, next slide. Right. So the idea here is to give you the why we want to do this hybrid parallelization, what it is, what we are using to do it, what are the challenges, give an overview of the implementation. So let's get into it. Next slide, please. So the main motivation for this is that with a hybrid parallel model, many algorithms simply work better. The main example that you see here on this convergence, on this comparison of the convergence rate is our multi-grid scheme. So these are all convergence of the same case with the same number of total cores, but using the hybrid parallelization, we're able to preserve the effectiveness of the multi-grid better. There are many other algorithms that can be a lot more efficient with this hybrid parallelization. So, for example, if you have a very large case and you're basically anything that requires global information from the whole domain. So you have things like transferring data across multi-physics interfaces, which is one of the examples I have there on the right. Other things like computing wall distances. At some point, some algorithms will not scale very well with just domain decomposition, and a hybrid approach gives you better results. Also, because with this we can reduce the communication overhead, which is an important factor to get strong scaling, which is something that will benefit medium scale optimizations where you're trying to take a maybe not very fine grid, but you're still trying to get results very quickly, or if you're running again some medium scale problem on in time domain where you don't parallelize at time usually. Next slide. So if that little teaser was enough to convince you to go and try this out, I will just let you know how to do it. So at the moment, what is covered by this implementation is a primal and forward algorithmic differentiation of compressible URANs and URANs FSI, and any subset of compressible URANs FSI. So just structural, just RANs, and steady, Euler, it has to be compressible. All those things are covered, and you can use just the normal primal solution or forward AD. The reverse mode AD is still in the works. And to use this, you need to compile the code with this special flag. So with OMP equal true, that's all you need to add when you compile the code. And then you can still run SU2 CFD as you would normally. So just call it with the config file, and this will pick up a number of threads from the environment. You can also customize this with the -t option, command line option. And so, for example, and this parameter changes the number of threads per MPI rank. So when you specify those things, the example I have there, so if you have 2 MPI ranks and you call SU2 asking for 4 threads, the total will be 8. There are some issues to have in consideration to get the best performance out of the code. So one is process binding with MPI. So you cannot bind, if you're launching these threads, you should not bind the MPI processes to individual cores. You should bind them to sockets or to nodes, but never to cores. And then finally, you can have slightly different results with this. So having 2 ranks of 4 nodes is not the same as having 4 ranks of 2 nodes. The guideline at the moment is to use MPI as much as possible, and then start increasing the number of threads as you notice that, for example, you have you think you have too much communication pressure on your network, or you see that, for example, the multi-grid is not working as well, things like that. So next slide, please. Oh, and the overhead of compiling with this and not using is very small. It's about 1% if you compile the code with this and then don't use the threads. So what is a hybrid parallel model? Traditionally, the parallelization is done through domain decomposition. That means that you take your entire domain, which is represented by the large square. You divide this in subdomains, partitions, that you then assign to different ranks, or traditionally processors. So then you need to create some ALO nodes for each of those subdomains, and you need to communicate some information across that with MPI. So to receive data from another place, from another place of the entire domain, needs 2 ranks to be involved in the communication. One needs to receive and the other one needs to send. In contrast with this, when we have threads have a global view of their subdomain. So they're represented here with kind of a little cloud to show that they can freely move over this domain and access any point automatically. Next. So the way that threads can interact with MPI in different manners. At the moment, we have what is called a funneled communication model. That means that the ranks have multiple threads, but only the main thread then communicates with the MPI. In contrast, you have multiple communication where any thread at any time can be making a call to MPI. And I show this crossed arrows here in the middle of the MPI layer to show that it doesn't have to be a one-to-one connection across the thread. So they just send any information, and any other thread can be the receiving thread. So that's a bit of work in progress. At the moment, we have the funnels, which is a little bit easier to understand and work with. And it doesn't seem to be much of a performance bottleneck. Next, please. Okay, so what we're using as our threading API is OpenMP. OpenMP is an API that gives a very simple and flexible interface to develop parallel applications. So parallel in the shared memory sense. So this sense that the threads can see all the data that can naturally have shared variables, as opposed to MPI, where you need to explicitly send data between the participants. So this little chunk of code is just a sample what you have. Basically, I'll throw around some terms here that will be important. So usually things that are declared outside a parallel region are shared by default. Then when we want to create some threads, we have this directive, pragma OMP parallel. This launches some threads, and so everything that is inside this parallel scope will be executed by multiple threads. Things that are variables that are declared inside that scope are private to each of the threads, and usually our parallelization will consist in distributing some work over these threads that we create. So in this example, I have a for loop. I want the different iterations of the for loop to be executed by different threads. Again, there's a pragma for this. It's the OMP4, and then we have special clauses for those pragmas to kind of fine tune their behavior. So you can here this work is distributed in a dynamic way. So it's scheduled dynamically in chunks of 32. So that means that one thread asks the runtime for a chunk of work, sized 32 indices, finishes, and when it finishes, asks for another one, and goes back and forth. So our idea is to use this API to distribute the work in the code. So all the loops that we have in the code, basically, and we want to distribute them using this approach. Next. So we mentioned how the different MPI ranks communicate and how the threads interact with that communication, but we haven't mentioned how the threads communicate between themselves. The answer is they don't really communicate. You simply have to be aware that sometimes there is a guarantee that the threads have a consistent view of memory, and sometimes they don't. So for example, I have a very simple, the classic parallel example here, the XP function. So that's taking y and adding a times x onto it. So we have a function here that does that, and x and y are supposed to be shared variables. When we enter this function, we have no guarantee that all the threads see main memory in a consistent memory, so in a consistent way. The way to enforce a consistent view is to have a barrier. So that's what you see there, pragma OMP barrier. You don't see this kind of barriers so much in MPI because they are implicit in a lot of the communication functions. But with OpenMP, it becomes necessary to have more explicit barriers to kind of force this synchronization. So after a barrier, there's a consistent view. We can then work on the arrays safely. Another interesting feature of OpenMP is that usually you can combine some of the directives. For example, we have the for work sharing directive here combined with SIMD. So SIMD means single instruction, multiple data, or vectorization. And we can use OpenMP to ask also for vectorization. So not only parallelization with threads, but also vectorization. And there are implicit barriers after a lot of the work sharing directives. So for example, after a for loop, there's an implicit barrier, and so after that loop finishes, all the threads involved will have a consistent view of the modified y variable in this case. Sometimes it's necessary to identify, or your algorithm needs to identify the threads or count how many are within a certain parallel region. For example, if you want to manually distribute work, that's done with those two convenience functions, get number of threads and get the thread number, and there's an equivalence there with the traditional size and MPI rank. Next. So an important distinction is this notion of shared and private variables. So things that are declared inside the parallel region are private, and each thread has its own stack. So that means that if you declare a static array, for example, in this case we have each thread has its own array of with 64 elements. The heap is a shared resource, and so it's available to all threads. But if we declare something inside, in the case where we declare here a vector and does dynamic allocation, so on the heap, but if we declare it inside the parallel region, we create 4 of them. And so that means if you then call our parallel function, our XP function, this will not do what we want. So because essentially we have 4 different X's and 4 different Y's, and the results of this computation will be different in each thread. So what's the strategy? Do we need to declare or allocate everything outside the parallel regions? It depends. So in general, the safe way, if you want a variable that is shared, it should be declared outside parallel regions. But we can still manipulate memory inside parallel regions. We just have to be careful that with things like allocation, only one thread should do the allocation of a shared variable. So you will see in the code this kind of pattern of having the master directive. That means that only the main thread does the operation. So the main thread does the resizing, and then you need a barrier, an explicit barrier, to make sure that all the threads see the resized array or vector in this case. Next. So the main challenge here with this hybrid parallel approach are data races. So if threads can see all the memory, we need to be careful that that 2 of them don't modify the same location at the same time. And this is very easy to happen with the common computation pattern we have in CFD, where grids are essentially graphs. That means they have edges connecting nodes, and those edges intersect at the nodes. And so if you try to process edges in parallel without any safeguard, you will very easily have a data race. So you can imagine that if you process edge A and edge B at the same time, and then try to update node P, you have a possible data race there. So there are a number of solutions to avoid this problem, and really the implementation of this hybrid parallelization is about avoiding this problem. There are built-in software solutions, and there are algorithmic solutions. Next. On the built-in solutions, we have atomic operations. That means that we modify a location of memory in a safe way. This is good, for example, for a reduction type of operation. We have the critical directive, which essentially serializes a given chunk of code. This is good, for example, if you're writing to a global resource like the output, like the console. And we have locks. Locks are essentially well, they are what the name says. When a thread acquires a lock, no other thread will be able to acquire that same lock, and so you can use it to protect individual resources. So you can, for example, imagine different files that you're writing to depending on the thread number, and you protect each individual write, each file with its own specific lock. So the pros here are that this requires relatively small modifications to the existing algorithms. But they have the problem of significant overhead and not very good scaling with resources that are used a lot. Next. Then on the algorithmic solutions, so the ones that require changing the algorithms, we could propose partitioning. So we could take the subdomains and repartition them the same way that we partition the global one, and then use strides on that. This is not really what we want, because we want to be able to explore dynamic load balancing of distributing the loops dynamically, which that is what gives this approach strong scaling. Then we have coloring, which consists in creating non-intersecting sets of entities, so edges in this case, but you can also think about elements for finite element codes. And this is basically, if you look at the grid coloring image I have there, if you imagine going over all the red edges first, and then going over all the blue edges, and then all the green edges, and all the yellow edges, if you do it in that order, there is no chance of intersecting. So this gives you fine-grained parallelization and enables load balancing, but it's bad for temporal locality. So you want to access, usually you want to access data that you've accessed recently, as that will make the best possible use of the cache of your processor. So what we do to still get good locality with this strategy is that we color groups of edges instead of single edges. So that's what you see there on the second image. We have this colored blocks now, so we process all the blocks colored with a given color. And in terms of code, what you will see as a repeating pattern is that we have an outer loop over the number of colors we have for the grid, and then within each color we need to process things in groups that are a multiple of the group size we use, because within each group we cannot process things in parallel. This is the default choice for the computationally intensive loops of the code. There's a config file option to fine-tune the size of the groups. It's this edge coloring group size, and the default is 512. Next. The other alternative to fix this issue is to do what people usually call scattered together transformations. So we have here on the left side an example of the typical edge loop. You go over the edges, you gather some information to compute something, and then you need to scatter that information to two different points, I point and J point. So you can also think of writing the code as a loop over the points, where you then loop over each of the neighbors, and that means that you only pull in information and you don't scatter anything. So this has the benefit of making embarrassingly parallel code. So you can imagine that you can have one thread per point working on this freely. If the code is not very compute intensive, so the downside here is that you need to repeat the computation basically. So if the code is not very compute intensive, this may actually give better performance, because it gives slightly better access pattern to memory. So you have fewer load and store of data. You have more computation, but you make use of the bandwidth a bit better if the loop is not very intensive. So this is what was done for all the pre-processing type of routines, and this is where a lot of code was changed. So computing gradients, limiters, sensors for GST, and so on. Those were all modified to this approach. Next. So the other way to do this scatter-gather, if you don't want to compute things twice, is to first compute everything for the edges. In step one, for example, computing all the fluxes for each edge, you keep that information, you store it, and then you do a second reduction loop where you go over points and neighboring edges, and you reduce that information. So this keeps the computational effort, but it adds this reduction loop that is bandwidth intensive, which is something that we could avoid. But as a fallback strategy, for when coloring fails, and coloring can fail. For example, if the ordering if the ordering of the grid is not too good, or if for agglomerated grids for multi-grid, there are a lot of intersections. You can easily have more than 30 edges connecting to a single point, and that creates too many colors, and at some point coloring might fail. So in a worst case, this is about 20% slower than coloring. And there's a bit of a work in progress here as well to kind of have another hybrid approach between this and coloring to get better performance. But the message is that the code will always work in parallel, and will always use all the threads that you request. It might just not do so as efficiently as all the time. Next. So in terms of overview of the implementation and the things you will see in the code, all the pragmas that are used are wrapped in this adder OMP underscore structure. So this is what allows us to disable everything when we don't compile with OpenMP, which is the default for now. So we have all these things defined in a header file. You can think of SU2 of the prefix SU2 underscore OMP as similar to the SU2 MPI wrapper, but for OpenMP instead. Next. You will only see threads being started, so you only see the parallel pragma in very select places, because we try to keep so that there's an overhead to starting the threads, and we try to keep that as low as possible, as reasonable, by starting them only once per iteration and integration. So we start the parallel region for the entire multi-grid iteration, and an entire one for each single grid iteration for example, turbulence models, and all the output and to screen or to write the results files is not multi-threaded. So that is all. It's parallel through MPI, but not through threads. So if we start the threads at this high level, then we need to make sure that everything that is called inside of this region is thread safe. So we have no unguarded writes, as I will show in the next slide. So you'll see this one object per thread as well in a few places. The main example is the numerics classes, where we need to create, so this object has some mutable state, and we need to write into the object before we can use them. And that means that they are not thread safe. So the way to use them in parallel by multiple threads is to just make copies, just have multiple ones. And then you will see this pick one numerics object per thread in a few places as well. Also, this kind of pattern of having some temporary variable that is allocated at class level, the example being solution I, residual, all these things that are still in the code, but in the solvers that are now hybrid parallel, they are not used anymore. And the reason simply being because we cannot share these things efficiently. We could think about creating one per thread as well, but then you get this thing, this fault sharing, where threads are using regions of memory that are too close together, and this actually decreases performance a lot. So the basic idea is that we cannot use, or any auxiliary variable that we use should be declared locally and not at class or at class scope. Next. So this the coloring and the fallback strategies that I mentioned, they are set up in the solver constructor. When the solver is created, the solver detects or tries to use coloring, computes a parallel efficiency based on the quality of the coloring. So if it sees that some threads would be just idling because they would not be able to get any work, it will switch automatically to the reduction strategy. And then in the code, you will just see very localized decisions between using one or the other. So it doesn't involve changing a lot of areas. Next. So then tricky areas. Another problem with or a possible problem with OpenMP is trying to avoid deadlock. So you have a deadlock anytime that one thread or some threads get to a barrier, but not all threads arrive at the barrier. And this means that, for example, if you have a barrier inside a conditional statement, you usually need to have two barriers, because you need to make sure that all the threads enter that statement before you make a change that can possibly affect the decision of entering the statement or not. And then you also have some not so obvious deadlocks. For example, when we use this work sharing directives, the 4 directives and so on, those routines are safe to use serially, sequentially. They are safe to use in parallel, but they cannot be used by a single thread of a parallel region. So there's 2 examples there that are fine, and then the third one where only one thread makes a call to the XP function in a parallel region will result in a deadlock because of those implicit barriers that those functions have. Even if it didn't result in a deadlock, it would result in wrong results just because of the way those work sharing directives work. So that's something to bear in mind. Once these routines are decorated with this work sharing constructs, they need to be used either completely sequentially or completely in parallel, and not something in between. Next. So the final not so nice piece of code, which we've managed to hide reasonably well in certain areas of the code, is to have potentially AD compatible funneled communication reductions. So basically what you see here is just getting the minimum element of something. So the line that does the work that you expect is line 7, where you get the minimum over a range. But because of this funneled communication, you actually have to first get a minimum across the threads within a rank. Then you need to communicate that with MPI, but only the master thread can do the communication. And this, of course, forces you to have 3 or 4 barriers just to make sure that everyone gets the same result all the time. So there's on line 2, I have something here when you really need to make a shared variable, and the only way to in a function, the only way to make a shared variable is to make it static, which makes it a global variable. So these are the examples of areas of the code where it would take a bit longer to wrap your head around them and so on. But this is fairly well hidden in things like dot products and so on. So you shouldn't see this a lot. Next. So finally, we have we have a fairly small or a very small set of OpenMP features. We use very few directives with not a lot of their capabilities. Also to eventually have this compatible with reverse mode AD. This is still enough to improve the scalability of the code. There are a few things that require a bit more care, but essentially it's just a matter, if you're developing the code, it's just a matter of not writing, or be careful when you write to shared variables. And there's still lots of working process. So there's more solvers to cover with the implementation. And the ones that are currently covered are essentially test bed for these strategies. It will take some time to cover everything, and we want to be sure that we have made good decisions. So we have made good decisions before we move to the next ones. And that's it. Thank you.
Okay, Pedro, thanks so much for the talk. So at this point, we're running a few minutes behind. So what we'd like to do is pause here for a 5-minute break. Well, we'll come right back at 8:40 a.m. Pacific time. So we'll start on schedule, on time. Unfortunately, we can't take questions, but please do leave them in the chat window. So in the question box, send them to us. We're going to record them and pass them on to the speakers so that they can take care of them and reach back out to you with the answers. So at this point, let's take a brief break. We'll be back at 8:40 a.m. PDT. Okay, in about 4 minutes. Thank you. Okay, thanks for rejoining us here. Let's get started right away on the next talk. So I'd like to introduce Daniel from Bosch, who will be talking to us about the work he's been doing on adjoint-based design optimization of pollutant emissions in heat exchangers. And I know how much effort he's been putting into this, so I'm very excited to see the results. So take it away, Daniel, if you can hear us okay.
Yeah, thank you very much for the introduction, Tom. The work that I show here today is really a team effort of the people that you see on the slide. So besides myself, Naiso Baisaisen from Bosch Thermotechnology, Travis Corrigan from Pointwise, and Tom Economon from the SU2 Foundation contributed a lot. And I already want to thank those guys. And today I talk about adjoint-based design optimization of pollutant emissions in heat exchangers. At Bosch, we developed natural gas boilers for domestic heating and hot water supply. And on the left-hand side here, you can see a wall-hanging appliance. And the core element in these boilers is the heat cell, of which you can see a CAD model on the right-hand side. In the full-length talk, I will go into more details. And in this lightning talk, I will just show some extract from the long version. So in this heat cell, chemically stored energy is converted into heat energy, and during the combustion process, harmful pollutants, especially carbon monoxide and nitric oxides, are formed. And it is of paramount importance to reduce those emissions. Furthermore, those emissions are strongly dependent on the heat exchanger geometry. So for example, when you take a look at those two geometries on the right-hand side here, those are cross-sections of the heat cell. And you see that in this highlighted area, the geometry is a little bit different. And just with this small geometry modification, you get very different CO emissions. So in fact, here we see a reduction of 47% in the experimental measurements. So this makes the emission reduction a major design driver for the heat exchanger. However, the formation of those pollutants are counteracting processes. So typically, when you reduce one, the other gets larger, and vice versa. On top of that, there are additional constraints in the development of those products. We want to have a high thermal efficiency. We want to have a low pressure drop for a good overall efficiency. And then there are plenty of manufacturing constraints, like material thicknesses, the casting process has to be possible in the first place, and so on. And we think that adjoint optimization is a powerful tool that can help us in overcome these challenges. So this brings me to the outline of my talk. I will first introduce the combustion model that we use in our optimizations. I will talk a little bit about the implementation in SU2, then shown exemplary application to an adjoint optimization cycle, and then show what we have planned for the rest of this year. Okay, so let's get started with the combustion modeling. One of the most accurate models for reactive flows are detailed chemistry simulations. And in these kind of simulations, you saw conservation equations very similar to those. And what makes those equations expensive is the species transport. And this is because you do not only have a bunch of those transport equations for all species that you take into account in your reaction mechanism, but all these equations are non-linearly coupled through the source term. So you see here in this term, there's the mass fraction that you want to solve for appearing here. And typically you end up with a stiff system that's expensive to solve. Furthermore, transport quantities become functions of the local gas composition, and typically mixing rules for those transport quantities, like viscosity, for example, are also not very cheap and surprisingly costly to calculate. In our case, we oftentimes, for example, use the GRI 2.11 mechanism from Berkeley, and this is not the largest one that you can use for methane combustion, but already this one contains 49 species and 277 elementary reaction, which makes the application of this model in a 3D geometry in an iterative design cycle very challenging. So what we do instead is we use a flamelet model, and the the basic idea of this model is to pre-compute one-dimensional flames with this detailed chemistry model, which are much cheaper to calculate because you have just one dimension. And then we parameterize the solutions as functions of the progress variable, which gives us the measure for the combustion process. And then the enthalpy, which accounts for heat loss effects that we see in the heat exchanger. So after those solutions are parameterized, we store everything in a large table, and we use this table in a lookup fashion in our 3D simulation that we run in SU2. And then we do not need to solve the chemistry, but we just look up all the quantities that we need as a function of the progress variable and the enthalpy here. So that means we only need to solve those two PDEs instead of the 49 PDEs, which we would solve in the detailed chemistry model. And we add two more equations here for the emissions, two transport equations for the emissions. How is this implemented? We implemented this model as a fluid model class. And if you want to look at our code, we published this in the feature flamelet branch. The branch is a little bit behind our current development, but we are planning to roll out an update until the end of this month, and then file pull requests for this later. And most of the magic in regard to the table lookups and so on happens in the set TDD state T function here. So here the table looks are performed, and we do a little bit more with the source terms. That's all in there. And the lookup table itself and the lookup routines are implemented in the lookup table class, which is based on the code that we got from Pedro and Matteo's group. And we took it and rewrote it. We made it a little bit more general. So if you want to use the two-dimensional lookup table, I think this is maybe a good solution already. It's basically very general, and you can use it for other purposes as well. The configuration in SU2 is shown on this slide. First, I wanted to state that the scalar solver that we use is implemented in the incompressible solver that Tom published in his paper this year. And the scalar solver is also written in a very generic way. So you can define an arbitrary number of scalars by setting the scalar names flag, and then you just give the scalar's name. So in our case here, we use enthalpy, progress variable, and then two more mass fractions for the emissions that we want to calculate. And then you can also provide source terms for those scalars. And because we have a special source term model for our species, we always have two contributions, a positive and a negative contribution. In the long-term version of this talk, I will talk a little bit more why we do this. And you can specify it with the scalar source term names flag here. You can also set those source terms to 0 by specifying null. And this way you can also model passive scalars with this framework. If you want to visualize data that's stored in your lookup table but is not part of the independent variables, you can add those variables to the lookup names flag. So for example, if you want to look at the molecular weight of the mixture, then you just add this name that you also use in the table data, in the table file here, and it will write out this field into the paraview files, and then you can visualize it. And then finally, the lookup table is specified, the file name is specified with the file name _LUT flag. Okay, let's come to the application. The test case that we use for validation and development is shown here. It's a very small two-dimensional geometry. The fuel and air mixture comes in from the left-hand side. A flame stabilizes on a burner wall that we model with a constant wall temperature of 450 K. And then the heat exchanger geometry is the simplified geometry, which looks like an oval. And we set the wall temperature to a constant of 400 K. And then we have the outlet on the right-hand side. We only simulate the symmetric upper half of the domain. And our optimization targets here is to reduce the pollutants, but also to reduce the average temperature on the outlet. And we do this in order to improve the thermal efficiency of the boiler. When we started to perform these optimizations, we saw that we have to deal with large mesh deformations, which led to some challenges. And one of those challenges was that the mesh deformation can lead to very bad mesh quality. And in order to resolve this, we implemented an automatic remeshing feature, and we teamed up with Pointwise and added this feature right after the shape optimization, shape deformation block in the simplified optimization cycle here. So in this block now, we take the deformed mesh, load it into Pointwise, check the mesh quality, and if the mesh quality is under a certain limit, then we remesh the geometry in Pointwise, write it out, and then continue the next cycle. This is realized with the glyph script. Glyph is the scripting language that you can use in Pointwise, and you would provide such a glyph script in your simulation directory. And besides this, you also provide the defaults file, which contains some settings, like, for example, the number of inflation layers that we use here, and so on. And then in the configuration file, you can enable this feature with the enable remeshing flag. So with this functionality, we were able actually to get some very nice results. And I show one optimization here. In the long version of this talk, you can see 5 different optimizations with different objective weights. And today, I'm only going to show the one where we optimize all 3 optimization targets. On the right-hand side, you see the baseline geometry, and the results that I'm going to show will be shown in this normalized plot, where you see the optimization targets normalized to the baseline geometry. So the baseline geometry would fall on this green line here, and the optimized geometry that we got looks like this. Also, in the long version of this talk, I will talk a little bit more about the physics, why this geometry looks like it looks. But you can see here that we were able to reduce the temperature on the outlet and also both pollutants, which is a very nice success for us. And this brings me to the outlook for the rest of this year. We also see that in our optimizations, it would be good to have more geometrical constraints, and we want to spend some effort in implementing a feature for geometrical constraints. Obviously, we are going to apply this to a more realistic 3-dimensional heat exchanger geometry. And for this, we also would like to include conjugate heat transfer. So there's already nice work going on in this field, and we are going to merge the conjugate heat transfer branch with the flamelet branch in the future. And then another big focus for the rest of this year is an implementation of a hydrogen combustion model. And the challenging step here is that hydrogen combustion usually is a little bit more complex in regard to diffusion processes, and we expect that we need to introduce a 3rd parameter in our tables, and this necessitates to implement 3-dimensional lookup tables and 3-dimensional lookup routines. So thank you for joining our talk today. Thank you also to the co-authors again. It was fun working together with you guys. And thank you for the organization of this nice conference. And with this, I'm happy to take any questions.
Thank you, Daniel, for the talk. So we're running a little tight. Thanks for fitting it in time. Unfortunately, let's not do questions live. Let's go ahead and transition to the next talk, but I do want to remind people just to leave questions in the question box there on GoToWebinar. We're going to export those and share them with the speakers so they can get back to you. So please do just leave questions there so we can keep moving. Okay, so I'd like to introduce, yeah, thanks again, Daniel. I'd like to introduce the next speaker is Beckett. He's going to be talking to us about the an overview of the aeroacoustic prediction and design capabilities in SU2. So take it away, Beckett.
Hello, everyone. My name is Beckett Zhou. So in my presentation, I hope to give you a quick overview on the aeroacoustic prediction and design capabilities in SU2, which we have been working on over the last few years. So since this is a 10-minute quick presentation, so I'll jump right in and show you the predictive capabilities as far as aeroacoustics is concerned. So for aeroacoustic prediction, the first step, of course, is the turbulent flow simulation to capture the noise generating mechanisms. In SU2 framework, we have a number of options. For example, URANS, EDDES with the new shear layer adaptive SGS, as well as the well-modeled LES, both of which you've seen hopefully in the last hour in the very nice presentation from Eduardo Molina from Stanford. And I would like to say that most of the these capabilities are possible because of his good work. And of course, we can also perform implicit LES simulation with the DG solver. So on the three pictures underneath, you see some of the test cases we've been working on. The first one is the tandem cylinder. The middle one is the delta wing, and the one on the right is a turbulent round jet. And most of these are done in very close collaboration with the Stanford group. For noise propagation to the far field, we use the Fox, Williams, and Hawkins acoustic analogy. This was initially implemented in wind tunnel formulation in my PhD thesis a couple of years ago, and recently we have extended it to the full so-called F1A formulation, which I'll touch on towards the end of this presentation. Okay, just one validation case. This is the tandem cylinder case from the bank workshop. So essentially, what you have is two cylinders. One is placed in the turbulent wake of the other, and this configuration has been studied in a series of experiments performed at NASA Langley. It is a prototype for interaction problems that are commonly encountered in airframe noise. For example, landing gear configurations. There are a number of important mechanisms that we need to capture for noise prediction. First one is the separation of turbulent boundary layer, then the free shear layer rolled up, as well as the interaction of unsteady wake of the upstream with the downstream cylinder. So on the figure on the top figure on the right, you see the Q criterion of the tandem cylinder colored by the vorticity magnitude. You can see the level of resolution we are able to achieve with the EDDES solver, and the noise source is then propagated to the far field with the FWH solver in SU2, and on the bottom figure you see the comparison with the experiment in terms of the overall sound pressure level, and the agreement, I believe, at all points are within 1 dB. So going beyond just the prediction, we are also interested in sensitivity analysis as well as optimization for in-air acoustics. And in SU2, this is achieved by an unsteady discrete adjoint framework. And here I've shown some equations that provides an overview of the framework. Essentially, J is the noise objective, evaluated within a certain time window, and alpha is the vector of design variables, U is the conservative variable, and G here is the governing equation written in the fixed point formalism. So we can express the Lagrangian associated with this constrained optimization problem, as you see here on the figure on the slide. And here we've added the adjoint state vector U bar at time level n. And if we go ahead and derive the first order optimality condition, we get these three equations. The first one is the state equation, and the second one is the adjoint equation that we are interested in. So if we go ahead and expand it out, we see that this is what the adjoint equation looks like. Essentially, it's another fixed point iterator with the contribution from the FWH module added to it, which is the DJ DU term, and this unsteady adjoint equation is then solved backwards in time to eventually get us the sensitivity gradient. And the highlighted term you see here are all computed using algorithmic differentiation in reverse mode, and we differentiate through the entire nonlinear iterator. Therefore, the adjoint iterator G bar inherits the same convergence property as the primal iterator. So if you're interested in further implementation details, I invite you to have a look at my colleague Tim Albring's paper from AIAA paper from 2016. This is an overview of the workflow of the noise prediction and optimization framework. First, we have the CFD solver to compute the noise source. Again, this is written in the fixed point form, and then the flow data on the FWH surface is then extracted and provided to the FWH solver, which computes the far field noise, far field pressure fluctuation P prime, and that's used to define our objective function. Then in the adjoint phase, the DJ DU term, which is the sensitivity of the noise objective with respect to the flow variables evaluated on the FWH surface, is then accumulated to the adjoint CFD solver to compute the adjoint variables U bar. Now a couple of examples. The first one is the minimization of rod airfoil interaction noise. And in here we have essentially a NACA 0012 airfoil section placed at a distance, a small distance behind an upstream cylinder. The near field noise source is computed using U-runs with a SA turbulence model. This is then propagated to the far field, to the three far field noise microphone positions with the FWH solver. The objective function is defined as the RMS of P prime averaged over three microphone positions, and we parameterize the airfoil section with 225 FFT control points to allow smooth morphing of the airfoil section. So the design question we ask the optimizer is to find the optimal shape of the airfoil section in order to reduce the interaction noise. So here are some results. The advantage of adjoint-based method is that it allows us to identify the regions of high design sensitivities, and that's what you see on the first figure. Here you see that near the nose region, the leading edge region of the airfoil, the sensitivity is very high, and as a result, what the optimizer does is that it does not collapse the airfoil, and instead it progressively adds more and more curvature round off the nose region as the optimization progresses. And we don't see any also span-wise variation in surface sensitivities here. This is the reason for that is we have very coherent vortices impinging on the airfoil leading edge due to the use of the URANS simulation. Nevertheless, the overall sound pressure level between the baseline and optimized configuration is shown on the last figure. On top here, we see that we have an omnidirectional noise reduction of up to about 6 dB. If you are interested in more details of this work, I invite you to look at our AIAA paper from 2017. Now, the next example is more focused on the broadband noise minimization. And in this case, we model the broadband noise source with RANS coupled with a stochastic noise generation model. There are many reasons why we choose to model the broadband noise source rather than resolving it with high fidelity simulations. And I invite you to look at our AIAA paper, and that it's discussed in more details there. Nevertheless, in this test case, we look at an ACA 12 single element wing section with a round tip, and it shows very similar underlying noise generation mechanism as that of a flap side edge. And here we use a RANS solution computed with SST turbulence model. The SNG module and its sensitivities are only evaluated in the tip region. Here you see in the box. We target the frequency range between 1 to 10 kilohertz, and we only allow the tip region to change. So the top one is the baseline design, and the bottom one is the optimized deformed design. Some comparison between the baseline and optimized design. The top two figures you see are the turbulence kinetic energy field. Near the tip region, you see a very drastic reduction on the TKE level. On the bottom row, the first two figures show the noise footprint, the surface noise footprint in terms of the log of RMS of P prime. And again, you see very drastic reduction of the noise source, surface noise source. And on the right is the far field SPL, and we do get a very clear reduction in the broadband range. What we are working on right now is that we're working hard to extend the existing FWH implementation to the full F1A formulation to account for moving sources. This is done in the framework of a NASA-funded project aimed at developing an adjoint-based noise minimization capabilities in particular for propeller and rotor configurations. And here I would like to acknowledge the PhD student from Dominion University, Omar Aika, who has done really good work in implementing this in version 6 of SU2 and
hey, Beckett, sorry to interrupt, just a 1-minute warning, okay?
This is the last slide. On the figure here, you see the comparison between the SU2 prediction and the NASA NOP2 prediction. We are gonna integrate this hopefully to version 7 this summer. And on the bottom, I'm just showing a so-called wish list in terms of future aeroacoustic development. And with that, I conclude my presentation. I thank you for your attention.
Excellent. Thanks so much, Beckett. So we're a little tight on time, so we're going to go ahead and start the transition. There were 1 or 2 questions that we'll forward to you, Beckett. There was a question about periodic boundary conditions and 1 or 2 other things, so we'll pass those along to you. But at this point, let's go ahead and transition to the next speaker, So we have Catarina, who's going to talk to us about the SU2 NEMO effort for non-equilibrium models for hypersonic flows using Mutation++. So go ahead when you're ready, Catarina.
Okay, hello everyone. So this presentation is about the branch SU2 NEMO, and this is, even though I'm doing this presentation, this is actually a collaborative effort between all of these people. So we have me, Marco Fossati, and Gabriel Banarescia from University of Strathclyde in Glasgow. Then we have Wally Meyer, Jacob Needles, Juan Alonso, and Brian Mungia from University of Stanford. Then we have also Thierry Majin and James Scoggins from Von Karman Institute of Fluid Dynamics, Thomas Economon from the SU2 Foundation, and finally Adrien Lozel from INRIA. So this is a branch that, as it focuses on the simulation of hypersonic flows, basically it needs to account for certain phenomena that are triggered at such high velocities, such as chemical reactions and thermal non-equilibrium. Therefore, we can no longer have the usual Navier-Stokes equations, but instead we need a mass equations, an equation for mass for the conservation of species for each chemical species, and also one extra equation for the conservation of vibrational energy. This has all been introduced in more detail in the developers meeting of last year, but I just wanted to give a quick overview. Also, this kind of flows cannot be considered as a perfect ideal gas anymore. So instead, we actually have to explicitly compute the properties of the chemical species. And this is done by a link with Mutation++, which is a thermochemistry library that provides all of these properties given a certain state of the flow. Okay, so the outline of the presentation is basically the achievements that we have been doing up to date. Then we will focus on the fact that we have been updating the NEMO branch to make it part of the develop branch. And finally, the roadmap for future work. So in this slide, we are basically showcasing some of the work that we have been done in the past. So in the first column, we show some images of studies that we were doing for purposes of verification and validation on the Apollo Common Capsule. And here we simulated flows with different Mach numbers and angles of attack, and we compared them to wind tunnel tests by the NASA databases. Then in the second column, we are showcasing the study that we did on shock interaction patterns over double wedge geometries in flows dominated by CO2. So here the purpose was really to study new physics, and we were comparing the shock interaction patterns obtained with CO2 flows to the ones that we would obtain if we considered instead a mixture of air. Then in the third column, we are showing some viscous simulations that have been done over the Bedford wing body. And in this case, we were actually able to use mesh adaptation thanks to the AMG library by INRIA. Finally, in the last column, here we are showing the validation of the Air 7 species model that has been recently added to SU2 NEMO. So we can also include ionization in our simulations. And here the results were validated against flight data from the RAM-C2 vehicle. Okay, so this is what has been done in the past, and now this year we actually have been focusing, as I said, in having the NEMO solver in the develop branch. And for this, one of the main things that has to be done is really the restructuring of all the files and classes, and this is what is shown in this schematics. So when it comes to solver and the output, we actually make use of what's already there for the usual flow solver, and we simply inherit from these classes to have the classes that are specific to the NEMO solver. But then when it comes to C variable, we inherit directly when it comes to CNEMO, Euler, and Navier-Stokes variable, we are inheriting directly from C variable. And also when it comes to numerics, since all the numerical methods have to be really specific for this new system of equations, that it's the non-equilibrium system of equations, we have a specific folder that deals with this. So this makes us now able to make use of all the generic routines available in the version 7 of SU2, for example, the computation of gradients, either for conservative or primitive variables, the computation of limiters, etc. And finally, we are also able to take advantage of all the improvements for performance that are now available, and this becomes even more essential for the NEMO solver, since by accounting for the chemical reactions and for the thermal non-equilibrium, we actually have a system of equations that it's larger from the usual Navier-Stokes. So with updating to the developed branch, there also comes the need for some regression test cases. So far, we have added 3 different test cases. So on the left side of the slide, we are showcasing a 0-dimensional heat bath. And here the purpose is really to isolate simply the non-equilibrium processes taking place. So these heat baths concern a mixture of atomic and molecular nitrogen, and we simply set the initial temperatures, vibrational temperature and translational temperature to different values, and we see how the system evolves over time. In the first picture, we freeze the chemistry. So basically this shows the evolution simply of the energy exchange between the translational and vibrational energy modes of the mixture. And then in the second picture, besides changing the input values for the translational temperature, so we have more chemistry triggered, we see a similar sort of kind of behavior, but instead we also have the impact of the chemical reactions going on. Then in the right part of the slide, we are showcasing the regression for a 2-dimensional test case. So here we have a single wedge with a 10-degree angle. So we simply have an oblique shock developing. So when we show the Mach number, basically we see that given that the non-equilibrium, so the angle is actually small, so the non-equilibrium doesn't have has a very small impact, and we can actually compare the post-shock state to the theory of oblique shock relations, and it matches very well. However, since we are explicitly considering the vibrational energy and temperature of the flow, in the second image we can see what's happening here. So basically what happens is that in the shock wave we have a sudden increase of translational temperature and translational energy, and what happens is sort of what's showcased in these heat baths. So slowly, after having a high translational energy, we have energy transfer to the vibrational modes, and which results in a gradual increase of vibrational temperature also in a 2-dimensional flow. So when it comes to roadmap for ongoing and future work, we can see this in 2 different ways. So when it comes to implementation, we are working on incorporating the class C-fluid model to handle all the computations associated with calculating the properties of the species, either thermodynamic, chemical, transport, etc. And at the same time, merging the link between SU2 and Mutation++, sorry, SU2 NEMO and Mutation++. And this is showed in a schematic. So basically, we will now have a new child of C-fluid model called C-NEMO mixture that will handle all of this, but we will have subchildren. So on one hand, we have C-Mutation TC-LIB, thermochemistry library, and this is the class that will have the link to Mutation itself, all the calls to Mutation. But then we also consider a C-user defined TC-LIB. So basically, this is any alternative way of computing this kind of properties, which can be, for example, a different library, but also, for example, hard-coded properties. Also, on the side of implementation, we have been working on the modeling of turbulence, so soon there will also be a NEMO RANS solver. Finally, in terms of physical modeling, we will implement different ways of considering the coupling for the non-equilibrium phenomena. So when it comes to vibration and chemistry coupling, we will also have preferential dissociation, and we will also account for the coupling between rotational and vibrational modes of the species. Last but not least, we are also doing some more work on expanding the ionization modeling in SU2 NEMO. So basically, this is it. Thank you for your attention, and any questions that you have, feel free to ask, please.
Okay, great. Thank you, Catarina. Nice talk. So we do have a few minutes for questions. So we have a good 5 minutes left, so we could do questions for a few minutes. There's one that's here already that I'll read out loud. So it asked, is there an AUSM PW plus unstructured version? Because it says that was mentioned in your slide. They're just curious.
If there's an unstructured version.
Yeah, so I think they're just asking if it's available within the solver. So maybe you could explain a little bit.
Yeah, so let me just go back to the slide that talks about that. Wait. Okay, so from all the methods that we list here, basically not all of them are already will already be available to work 100%. So the ones that are more ready to use, besides the ones regarding diffusion and source terms, because those are essential anyway. We have a USM working 100%, and then also the row scheme. When it comes to MSW centered schemes, and also a USM PW plus, that the one you're talking about, and plus UP2, these are numerical methods that will still need some more work, especially when it comes to the link to Mutation++.
Okay, that sounds good. But just a note that it is available if you're just running the perfect gas version of the solver. It should work fine, but not here in the context of NEMO yet. Okay, so there's another question. Actually, there are a few. So the next one is there a timeline for this branch to be part of the develop branch, so to be released into develop?
That's the $1,000,000 question. What's the timeline? So we already opened the pull request, so we are really now working on incorporating all the feedback from different developers that are providing it. So I would say that in the next 3 months, this process will be more completed, and I think by then we can have the NEMO solver available in the develop branch.
Yeah, I'm very excited to see that the pull request is open. So another question is, any intention to include the MHD equations?
Sorry, what is NHD equations? What goes NHD?
Magnetohydrodynamics. It might be out of the scope of this presentation or this talk, but.
So actually, this is one of the questions. I can actually pass the word to Marco Fossati because he's actually more in charge of the long-term future plans. So I don't know if he wants to say a word about this or not.
Yes, can you hear me?
Yeah,
yes.
Sounds good, Marco. Go ahead.
Yeah, thank you, Catarina. Yes, the answer to the question is yes. It is on the roadmap of the development of NEMO, not in the medium term, but there will be something that will be started to be developed along that line, coupling it with the work that Catarina mentioned about ionization.
Okay, great. Yeah, there are a couple more people are very interested in these topics, so a couple more quick ones. The last slide mentioned inclusion of ionization models, and they want to know if they could use it to model lightning propagation in air, the models that you have in mind.
Okay, so actually that question I will also pass to Jacob Needles because he's the main person in charge of ionization. So if we could actually answer to this question.
Sure. Can everybody hear me?
Yeah.
Great.
Sounds good.
Yeah. So that is not something we've looked at, and at least on my end, I'm not completely familiar with maybe some of the boundary conditions that we would need to look at modeling like lightning propagation. So far, we've primarily been looking at flow fields around entry vehicles. So for example, Catarina mentioned the Ram C2 flight experiment. So it's something we'd have to look at more and see if there's anything additional we would need to add. But I think potentially capturing those kinds of physics effects are definitely on the roadmap, as Marco mentioned.
Okay, great. Thanks, Jacob. So in the interest of time here, we'll have to stop and start transitioning to the next presentation. But there are a few more questions. We'll go ahead and forward those questions to you guys that were just speaking, the NEMO folks, and you guys can take it offline. So
Thank you.
Next, I want to, thanks again, Catarina. Very nice job. I want to introduce next Akshay, who's going to speak to us about the effect of roughness on wind turbine performance. And I should say he's also been doing quite a bit of work on the pressure-based incompressible solver. So go ahead, Akshay, when you're ready. Take it away.
Hello, everyone. Am I audible? Yeah. So, hello, I'm Akshay. I'm doing my PhD on wind turbine aerodynamics mainly, and like Tom mentioned, I primarily work on pressure-based solver in SU2, but today I'm going to talk briefly on the modeling leading edge erosion and today I'd like to talk about modeling leading edge erosion of wind turbines and how to model that in SU2. So, so the first, sorry, there's a bit of a lag in the. Leading edge erosion in wind turbines, it occurs mainly due to exposure to the environment. So during the operational conditions, the turbine is pretty much exposed to all elements of the environment like rain, hailstones, impact of insects, dust, and so on, and especially in offshore conditions where you have a lot of these conditions, and this can lead to chipping away of surfaces of the turbine blades, which leads in reduction of the aerodynamic performance. And in order to quantify, or in order to first eliminate this performance, we first need to quantify this, and this is usually done by modeling these turbine blades as a rough surface. And generally, rough surfaces are represented by a roughness height K. So this roughness height you can either estimate based on some impact models of rain, or by even some scanning devices to the turbine blades itself. So, and once you have this roughness height K, usually in order to model them in CFD or in RANs in general, we need to convert that into a equivalent sand grain roughness. And this equivalent sand grain roughness, as the name implies, is the equivalent sand grain distribution of a realistic roughness distribution that gives the same pressure loss. And there are a lot of empirical relations to go from one to the other. And depending on this sand grain roughness, you have a different effect on the flow. Primarily, this manifests as a shift in the boundary layer. So if you sort of zoom into the wall region, so in the near wall region, so here you can see the plot of the viscous sublayer in the log region, and so essentially depending on the value of this equivalent sand grain roughness, you have a shift in the velocity profile, and this shift in the velocity profile manifests as early separation or increase in skin friction drag, and which can have a lot of adverse effects on the wind turbine performance and in general aerodynamic performance. And in order to model this shift in RANS models, usually we modify the turbulence boundary conditions that are applied at the wall. So the two models that are available in SU2 are the SA and the SST shear stress model. So for SA, we essentially assume that at the wall, instead of applying a zero turbulent viscosity condition, that there is a shift. So the mesh you make is like assumed to be a virtual wall that exists on top of the roughness elements. So you have a non-zero viscosity. So you have to make slight modification to the boundary condition that's applied. And because of this virtual wall, also a modification to how this wall distance is computed throughout the turbulence model. There are some more modifications that arise because of this wall distance computation that I have not listed here, which I mean, you can find them on the internet or in the literature. In SST, the modification is slightly more straightforward. So essentially, when you're solving the K omega SST equations, you assume that at the wall, the omega tends to infinity, so you assign a very large value. But when you have this rough walls, there is no virtual wall concept here, but you just say there is a non-zero viscosity, and you present a finite value of omega. And this finite value depends on your roughness height. And there are many different models available to do this, to calculate this finite value and many corrections and so on. But in SU2 at the moment, there are the two basic models are available. So the first one is the SA model that I just described, and the SST model that was originally developed by Wilcox. So both of these models are available in the branch feature rough wall. I opened a pull request some time ago, but yeah, and I'm in the process of attending to all the reviews, and I've received some very useful comments from developers. So I'm in the process of incorporating this branch into develop. But to just give you a brief overview on how you would, in theory, use this. So assuming you have an airfoil and you want to model leading edge erosion, or for that matter any erosion, you would basically separate the wall surface into a smooth and a rough part, and give them with different names, of course, and you specify the sand grain roughness in your config file. And with this sand grain roughness, a different boundary condition is applied to the rough part as opposed to the smooth part. The exact way this will be implemented in the config file is still under review. I have received some very useful comments from Pedro so far, and Tim as well. So in case anyone else is interested, you can always look at this pull request and weigh in with your opinions and comments as well. So this is, I mean, the implementation is fairly straightforward. It's just a modification of the boundary condition. And now I just move on to some validation results. So the first one is a flow over flat plate, very traditional case. So the first thing I want to do is verify the roughness models against the theoretical predictions of the shift in the velocity in the boundary layer. So on the right here, you see the shift predicted by the SA turbulence model, and on the left, you have the SST turbulence model. So the solid lines are basically the numerical results from SU2, and the dotted lines are the theoretical predictions. The most obvious thing that you would see here is that the SA model is somehow more consistently performing better than SST, especially when you look at the fully rough conditions where you have very large roughness elements. And this is a sort of a well-known deficiency in the roughness model in SST. And there are some corrections proposed, but those corrections are not implemented as of now in SU2. So to further validate this against an experimental result, so here I'm plotting skin friction computed by both SA and SST against an experimental data. I've also added the clean skin friction just as a reference. So as you can see, both the models do predict that there is an increase in skin friction because of roughness, but once again, the SA roughness model tends to do much better than SST, and it's pretty much on top of the experimental results. So, I mean, this moving forward in the next few slides, I'll mainly present results from the SA model and not focus on the SST. Here is a very qualitative description of what happens when you have some roughness on an airfoil. I have some experimental results, but I haven't presented here because of time constraints. But essentially here, what you're seeing is the pressure plot on a 15% thick airfoil. And the one in brown you see is the clean conditions, but there's no erosion at all. And once we start, once you assume that the airfoil is getting eroded, there is a separation happening, and this location of separation increases as we increase so the amount of roughness that is present on the airfoil. Now this onset of separation has a major role when you're dealing with wind turbine performance, because I mean, it can lead to stalling, and which can be quite dangerous when you're operating overseas on offshore conditions. But in order to quantify this more nicely, So the idea is to look at what happens on an actual turbine rotor itself. To do this, I've chosen the Avatar turbine rotor. So the Avatar turbine rotor was the Avatar project was a EU project that was the TNO was also a part of, and basically there is a reference turbine blade that was designed that is about 100 meters long, and the rotor consists of 5 different airfoil sections. At the root, you have the 60% almost cylinder type airfoil, and as we go towards the tip, you have thinner and thinner airfoil region. So in the midboard section, you have about 30% and 35% thickness, and go closer to the root, you have 60% thickness. And in order to find this power produced by this turbine, I use a combination of SU2 and an in-house blade element momentum theory tool. So this BEM tool basically uses the sectional aerodynamic information from SU2 to compute the overall power output, and there's also you can also do annual energy performance and so on. But first focusing on the sectional information. So here I just give you some results on the DU300. So this airfoil is in the midboard section. It's a 30% thick airfoil. So here we are looking at some efficiency plots with angle of attack. So on this picture is basically assuming only about 1.5% of that. So very small region in the leading edge is now considered to be eroded. And as you can see there's not much change in the aerodynamic efficiency in the lower angles of attack. So, and this is usually where this region of the turbine blade operates. We don't see much of a drop here, but when you go slightly higher, you have a drop of in performance. But when you increase the span of the roughness, even at a lower roughness levels, even the design conditions are deteriorating further. And in order to carry this, use this information to do this for the whole turbine rotor, I assume the midboard section, basically the 30% thick and the 35% thick airfoil are eroded, and assuming again about 1.5% of the airfoil is eroded. So, and this roughness values is basically for demonstrative purposes, and it's essentially ensuring that the flow is not turbulent, it's always turbulent, and there is no laminar region. And using our BOT or the blade optimization tool, we noticed that there can be up to about 2.5% drop in the power produced when you have the entire midboard section to be rough. And depending on how far the roughness section exceeds, so if it's closer to the tip, there is a larger drop off in power, but if it's closer to the root, there is not as much drop in the power produced by the wind turbines. So, I mean, this was a very short presentation. The idea is to just demonstrate that there is a roughness model in SU2 and that you can use it for your applications. And in future, I mean, I haven't shown you a lot of results here because I wanted to keep it short. There are a lot of other validations that I've done against experimental data, which we can discuss in future. And moving on, the other thing, another wish list, so to say, is to incorporate a transition effect of roughness on transition modeling and incorporate all the corrections to the SST roughness models, and and probably even full rotor 3D RAN simulations with roughness. So yeah, that's about it for the roughness. Thank you for your time. Thank you for your attention and any questions.
Okay, great. Thank you, Akshay. We do have a couple questions, maybe just time for one while we transition. So I'll just read one out loud and we'll forward you the other ones. This question asks, how does your pressure-based solver implementation compare to the density-based solver or the preconditioning-based approaches in terms of convergence, etc.?
Oh, okay. I think I probably should mention it here. This roughness model is not in the pressure-based solver. It's in the turbulent solver, so it's available in the density-based. And coming to the question, the pressure-based solver is a separate branch called feature pressure-based. And that is, yeah, I mean, we do with the usual momentum and the Poisson solver with a simple algorithm and the Piso algorithm and so on. So that is a separate work in progress that's not exactly related to the roughness model. So the roughness model is independent of.
Okay, great, thank you. Thanks again for your presentation, Akshay. So now I'd like to start the transition to our final lightning talk for the day. So Ruben will join us, and he's one of the directors of the foundation. He's going to be talking about coupled adjoint sensitivities and problems involving turbulent flows, radiation, and conjugate heat transfer. So once you're ready, Ruben, I see you. Go ahead and take it away.
Can you hear me? It's all right?
Yes.
Great. Thank you. I think, can I get the control of the, I have the control, right? Great. So thanks Tom for the introduction. So I'm here in representation of all this group of people here. I was at the Technical University of Kaiserslautern until just before the COVID, and I'm right now on a very cool company, but somewhere else. I'm in A Coruña here, and also as Tom was mentioning, I'm one of the directors of the SU2 Foundation. And today I'm going to tell you a little bit about a project that I was working on and that now was taken by Nicholas and Thomas in shape optimization for phosphate productions. And we, of course, we're using SU2 for this. So hopefully this, okay, great. Just to motivate our work, this here is a plot, and maybe some of you speak better German than I do, but this here is a plot about heat consumption or heat requirement for different sectors, right? So we have industry, we have households, etc. And of course, now in terms of a transition to a greener economy that should happen sometime after this pandemic, we will try to reduce this because that, of course, has a pretty high consumption of energy. And in this case, we're going to focus on the the heat consumption for process for industry, or like for process industry. So we put together a project that started 3 years ago, almost 3 years ago, financed by the Ministry of Education and Research of Germany. And that has the partners of a company that is ICL and a couple of academic partners and Fraunhofer. This project was EFO, and these are the members of the project. I was here. This picture, I think, was taken a couple of years ago. And the idea for ICL and the interest from an academic point of view is to be able to optimize a furnace such as this one here, that is used for the production of phosphates for the food industry. So there is an inflow of phosphoric acid and an outflow of phosphates, and the flame and the heat introduced into the system is able to produce a series of chemical reactions that lead to the production of the byproduct the product that we are interested in. So we have a simplified model here, in which you have a chimney and a series of walls. There's here like a melt, so it's not exactly a solid, although you'll see later that we model it as a solid. And there is the flame, and there's a relatively high heat involved in this system, right? So the temperatures are pretty high. So one of the important things that we need to take into account is we need to introduce the radiation into the system. So the radiative heat transfer equation is this one that I'm presenting here for 2D. And the complexity behind this equation is that it's a 5-dimensional phase space that has infinite spectrum of wavelengths and also all of the directions in space. So solving this equation is particularly complex, and there's a lot of research going on only in solving this equation. What we're interested in, is solving this equation coupled with the fluid equation and also eventually with the turbulent equation. and also with conjugate heat transfer. So in order to do that, we simplify the model and we go for an approximate model, which is the P1 equation, which is as explained here, is an asymptotic expansion of the RTE using an anomaly series. And basically this reduces the system to a one equation model that depends on the radiative energy, with a couple of just parameters depending on the participating media, which is this absorption coefficient and this scattering coefficient, and also a black body intensity term that couples the radiation model with the fluid model. In order to test this problem in a setting that is relatively similar to the one that we have in our furnace, we have started, and this is still ongoing work, but we have started with a simplified model in which we have a cavity that has buoyancy, which a hotter wall right here that is with a fixed temperature of 600 Kelvin, and then we have a solid right here, which starts off and has these three boundaries at 300 Kelvin. Then we have an inlet, and we will simulate a flame here as a heat source. And due to the natural buoyancy of the system will start rotating in this direction due to the gravity as well. The idea is that we want to maximize the heat flux through this boundary, this CHT boundary, so that we can, for a given amount of energy that we put into the system, we can maximize the throughput. So we can maximize how we heat up the solid, which is what will induce the chemical reactions that I was showing you earlier in the melt. So as a first approximation, we have simulated this. So as I was saying, this is a simplified heat source here that simulates the, that simulates the effects of the flame. There's an inlet and an outlet. There's the conjugate heat transfer through this wall, and this is the solid here. The distribution of temperatures here varies from 300 to 750 Kelvin, and this introduces a convective situation into this cavity. What happens is, of course, as the air is hotter here, it's heating up the solid, and you can barely see it here, but it's heating up the solid through the heat boundary. So the idea that we have is, okay, we want to compute couple adjoints. We're going to compute couple adjoints in this upper and lower boundary. And our idea is to be able to optimize this simplified furnace and later on the real furnace for its shape. So we minimize the amount of heat or the amount of energy that we need to pump into the system while keeping the same amount of product. In order to do that, we are computing, as I was saying, the couple adjoints. So we have a situation in which we have the Navier-Stokes equations that are coupled with the radiative heat transfer equation, or the P1 model here in this flow domain. We have here this solid domain that is the heat equation is computed there, and we have a CHT boundary right there. This is not exactly an optimized geometry, but rather this is just a naive implementation of taking the gradients that we compute with the FFD box and using those gradients to do a naive implementation of how an optimized geometry will look like that will maximize the heat transfer through this boundary. I'm saying it's not an optimized geometry yet because it's the engine that will optimize problems with multiple zones, etc. is still under development right now. So just to summarize, and this was just a very small insight into the project. The idea is that we will be putting a paper on the proceedings that will explain better how all this couple model works. But the idea is that we have implemented a multiphysics model that simulates these high temperature processes that are similar to the furnace that we want to optimize at the end of the day. And given our experience that shape optimization using automatic differentiation gives very good results in other areas, plus the models that we have added into SU2, we're confident that we will be able to produce an adequate solution to this problem. Also, this has a very large potential for other industrial applications that involve high temperature processes. The implementation, this is something I forgot to say, the implementation is modular. This P1 model is implemented such as a turbulence model. So it's fully modular, it can be turned on and off, and it can be extended with other radiation models in case that is considered worth. And then another of the goals of the project is to be able to compare discrete and continuous approaches because of the work that our colleagues at the mathematics department are doing. So that's all from my side, and thanks for listening. And if you have any questions, just please go ahead.
Great, thank you, Ruben. Excellent talk. So we have plenty of time for a few questions. So if folks have any, please drop them in the question bar. There was at least one comment that people like your cat, Ruben. So.
Oh yeah, the cat is always there. She likes the window, so she's just always wandering around.
Very good. Let's see. Any technical questions? Please drop them in the box at the moment. Nothing specific yet. I think you can also probably see these questions if they pop up, Ruben.
Yeah, and, there should be a question there, question box.
Okay, we'll give it a minute. Okay, here comes one. I'll read it out loud. Is the adjoint calculated in the solid part?
So the adjoint is calculated in the couple model. So the adjoint is, so we are using the CHT adjoint that Ole implemented some time ago, and we are coupling it with the radiation only. The radiation is only on the CFD part, though. It's only on the flow side. But the adjoint is coupled. It's not just the adjoint of the flow domain, but rather the coupled adjoint.
Excellent. So there are a couple more. Someone asks, what optimization solver is used? So what optimizer are you using?
So no, as I was saying earlier, the optimization engine is still being developed. So right now it's only using the adjoints. So just taking the gradients and assuming, okay, this could work for this particular case. But there's no optimization, although that was a misunderstanding with our colleagues because they prepare the slides. But the optimization engine for the coupled, given that we need the coupled adjoint, that requires some changes in the engine that we have for just airfoils, and that's still being developed. That's not there yet.
I see. So you were taking the sensitivities and just taking, say, one step like a descent or something, and perturbing the geometry.
I just took the sensitivities, and I figure, okay, I impose here also that that was a while ago, and I wouldn't even call this like an optimized, but rather a naive change. I don't know if I don't have the control anymore, but yeah, it was basically you impose some conditions, and then you assume, okay, I just take the gradients and make sure that the numbers they make sense. But the numbers of the gradients were verified for the CFD domain. That's a paper that we put last year in the proceedings of IKEM, and that's a paper that will be out there relatively soon. And that's for the coupled radiation model with the CFD, and then the adjoints are just an extension of that.
Okay, very good. We still have a minute or two for questions if anybody would like to ask further questions. Okay, while we wait for that, actually, it looks like we have one more. This might be better served for the discussion we're about to have. So why don't we go ahead and start a transition. So Ruben, thanks again for a great talk. What we're going to do here at the end in this final session is it's meant to be open-ended discussion of really anything that people would like to speak with the SU2 team about. So what I would like to do is invite anybody who's a panelist that we've had logged in as a panelist, the speakers. If you're okay with it, turn on your webcams, and we'd like to have you all available. And what we can do is, just like people were doing at the end of the talks, is post any questions from the audience that you guys want answered in the window, and we'll just do our best, kind of round robin style, to answer some of these questions as we go. So this is meant to be a little bit informal, just discussion time. So let me also turn mine on. Okay. Very good. Starting to see some more folks. Okay, I think there's already a first question we can start with while other folks are turning on cameras and getting involved. So I think maybe this is a good question for Marco, if you can see this. There's a student who is interested in code development for the PhD. Basically, they're interested in working with the SU2 NEMO team. So I'm interested in plasma physics and optics. So maybe we need to unmute. Sorry, Marco, 1 second.
Yeah, okay. Thank you, Tom. Now I guess that people can hear me. Yes, I was wondering if he's the same person who posted the question on the panelist, and I said that I would definitely be interested to have a chat. We can maybe get in contact. I don't know if you can write me an email. I can pop an email somewhere on the chat to him, and then we can bring it forward. But definitely, yes.
Okay, very good. We've actually had a few people now ask this question, and I think we can probably postpone it maybe for Friday in a deeper discussion, but several folks have expressed interest in CUDA support within SU2. I don't know if anybody wants to comment on that now, or if we save it for Friday.
Well, Tom, I'll say something. I think it's a unique opportunity that we haven't been paying much attention to in the SU2 community, but I think on Friday, as feature development, is certainly one of the topics we ought to talk about. I think the opportunities for faster performance of the code are obviously there, and we've seen them in many efforts in the community, and it just cannot be disregarded. We just haven't had the time or the know-how to do it up to now, right?
Right. I think it's a good point. So yeah, maybe if you're available to chat on Friday or to join the discussion on Friday, we can maybe go into a little more depth. Okay, questions are starting to pile in, so let me do my best at sort of doling them out here. I might ask certain people to chime in. So the next one is someone asking, they're interested in exploring SU2 for applications in FSI, fluid structure interaction, and they're wondering if anyone is interested in collaborating. So I think there are a number of people working on FSI here on the call, Ruben and Nico and Rafa and Pedro are there. Anybody want to jump in?
Yeah, what does collaborating mean?
Well, that's a good question. It sounds like you're open to it. Maybe if you just say a word about what you guys are doing. I don't know that everybody's aware of what is available in the code right now in FSI, and what's being developed.
We can do pretty much anything with FSI. So the only thing that the one thing we cannot do and will be able to do shortly is adjoints in time domain of FSI problems. Catarina is working on that. Other than that, we can do a lot already. So it depends on the particular flavor of fluid structure interaction that people want to explore. If you want to couple SU2 with an external FEA solver, there's also people working on that. So yeah.
If I may add to that, at Stanford we started recently a program with the Air Force and Northrop Grumman, and the idea there is to also have the ability to couple Nastran to SU2 through the Python interface for both analysis and sensitivity. So everything is open sourced. So if anybody's interested, let us know as well, and we'll love to collaborate it in many different ways.
Okay, fantastic. Let's keep moving. There are still more questions running in. So Ruben, this one I think is probably best for you. What numerical fluxes are used for the P1 solver that you presented? Oh, you're muted.
It's just a viscous. It's a viscous equation. So it's just a one. It's very similar to the implementation of the viscous term of the Navier-Stokes equation. With a one,
Okay.
with a one
average of gradients.
Yeah,
style.
so it's an average. It's an average gradients with a correction. There's nothing too fancy there. It's more fancy in terms of coupling, being able to couple that with all of the other terms at the same time.
And that's available now in the develop branch, right? And I think you
No, that's actually released.
Yeah.
That's in the master.
Oh yeah, in the release.
Yeah, that was released I think like 4 months ago. So right before I moved to Spain and I got stuck here.
Yeah.
Tom, here's a question for you. Maybe there's somebody from the audience saying that most of the applications that we've seen so far today are for the simulation of gases, but what about liquid flow?
Yeah, so I would say a couple things about that. The density-based incompressible solver that's available, that's in the master version, has been released, can treat liquids just fine. So there are 1 or 2 examples in the test cases of this. I think I have a water test case and maybe 1 or 2 other that are liquids, so that works well. And then I think if Akshay is still on the line, I believe the pressure-based solver that he's been working on will also have no problem at all handling liquids, of course. So if you go to the test cases, there should be 1 or 2 off the website, so you can go and take a look in the incompressible flows section. Okay, there's well, yeah, there are a ton of questions. So somebody's asking, what's the latest status of the turbo machinery capabilities in the code? Let's see if I think we have Nitish online. I think you're going to see a presentation on Friday. If we can't get Nitish on, maybe we just postpone that one for Friday. Let's see. Okay, let's keep moving. Here's the
There are
next
a few
one.
questions about meshing. I don't know if you've seen them, at least 2 of them, regarding meshing with open source tools. So I don't know if anybody in the panel wants to comment about use of Gmesh for mesh generation. We talked a lot about Pointwise because many of us have access to it, but how about using open source tools for generating meshes for many of these calculations?
Yeah, go ahead, Marco, if you're. You're muted again.
Okay, thank you. Yes, so we have been using Gmesh. So all the examples that Catarina presented during the presentation today, as well as other examples that are available on the more extended presentation on NEMO Online, were done using Gmesh as the baseline mesh generator. So this is something that we've been doing. One other element that we have started doing, but on the side of NEMO, was to use Gmesh for doing automatic mesh regeneration, where you're changing the topology of your domain. So we are still at the beginning of it, and we cannot say more than that on the show a lot of results, but there is something that so far is working fine. So the question is yes. The answer to the question is yes. Gmesh works fine. Maybe there are problems where the geometry, the complexity of the geometry may not be well suited for Gmesh, but these meshes were all viscous, so
So as a follow-up to that, Marco and others, somebody asked, any guidelines have evolved for, are there any guidelines that have evolved for mesh quality metrics? Few quality parameter definitions have been recently in SU2. Pointwise also has some quality metrics for the dual grid in recent versions, and I guess the person asking the question says that it's important from the point of view of very complex industrial applications. So I'll begin by saying that in the scale resolving part, Eduardo, who I don't know if he's online now at the moment, but he can unmute himself if he wants to, has provided some just sort of basic information as to what needs to be done for those types of simulations. But I think in general, others can probably comment about mesh quality metrics.
Yeah, if Eduardo wants to jump in too, he can. I would just add a comment that maybe about within the last year, maybe 6 or 8 months ago, we did start reporting some basic mesh metrics. So we have an orthogonality measure, an aspect ratio measure, and a volume ratio measure. And those are very much in line with what people typically do for those things. It's similar to what you might find in Pointwise or other commercial codes. But it's limited to just those 3 for right now. But the code will report that when it starts the pre-processing at the beginning. But maybe if Eduardo, if you're still there, maybe you have a comment about your meshes and your cases you showed.
Yes, I have a comment, and I'm following just the metrics of Pointwise, but I think we need to have our own metrics. For example, what is the limit of orthogonality and the limits of the angles between the cells that SU2 will converge? This is something that we need to address in the future. But what I'm doing, I'm just following the guidelines of Pointwise for now.
So I'll also add that I think in Brian Munguia's presentation on the last day, because of the use of highly anisotropic meshes and the mesh adaptation work that he's been doing in collaboration with others, there have been some changes to the solver in order to improve robustness. And I think the mesh quality metrics are really important in that domain. So the person who asked that question should probably look at that presentation as well and get in touch with some of the authors of that one. There's one here that I think is, since Nico is there, maybe very well suited for him. One of the people online asked, are you still looking into improving adjoint capabilities, whether it is efficiency for the linear solver or more complex configurations or including the Hessian matrix in the optimization process? So maybe you can comment on that, Nico.
Oh, maybe you're muted again.
Yes, of course, we always work on the improvement. First of all, because our algorithmic differentiation tool is linked with SU2. So, for example, you saw the talk from Pedro about the OpenMP stuff. So it's not so trivial to realize this with AD, but we are working on that and hope to provide full capabilities soon. And yeah, that's what I can say from the algorithmic differentiation point of view. And there are a lot of specialties we can do based on these fixed point ansatz. We have other things published in the past. This is maybe just one should know about it. These recursive projection methods. Sometimes you have divergence problems. Also, you shouldn't have them, but we have methodologies to overcome this. Yeah. And I mean, everything which speeds up the solve speeds up the adjoint too. So usually we should inherit perfectly, at least in iteration counts, the convergence rate of the primal solver. Yeah.
Thanks, Nico. There are a couple questions that I'll just take quickly because they're a little bit simpler. So some folks have asked how to get involved or how to get started if they're new with the code. I would say the best resource is if you go to our project page, su2code.github.io, we have sets of tutorials and sets of documentation. So I think if you go through the documentation there and then you run through the sets of tutorials you find, you'll be up to speed in just a few hours on the code. At least, as a user, you'll be familiar with the config files, how to set up runs, how to build, etc. So take a look at that. And then there's another question, which is pretty easy. I think Tim's here. Maybe he can say a word about it. I'll put you on the spot. Somebody's asked about whether we have a Slack channel. So take a look at that. And then there's another question, which is pretty easy. I think Tim's here. Maybe he can say a word about it. I'll put you on the spot. Somebody's asked. I don't know if it's going to work. I shouldn't have put Tim on the spot, so I'm gonna I'm gonna mute you. So the short answer is yes, we have a Slack channel. We can share the link on here, and we happily invite people to join the general channel and share with us. We've had people joining the past couple months for various reasons, and it's another opportunity to plug the fact that we have weekly developer calls now. So over the last month or two, on Wednesday mornings at 7 a.m. Pacific time, so at the same time we would have started this morning, we get together and just chat about the latest pull requests that are open, things that people want to change, proposals for modifications, even just simple questions if folks are having trouble. So feel free to A, join Slack, find us on there, and B, if you want to get involved on development, anybody can join those calls and ask questions.
Tom, it may be worthwhile reminding people to CFD Online, not as interactive as Slack, but place to ask questions.
Yep, that's still linked off the main web page, the project page. And yeah, we do our best to keep up to date with that, but even if we're not as active any longer, there's still a lot of good information in there. So if you go and search, you'll find a lot of old posts with good info. Okay, let's look for, there's a question now. Eduardo, since you're here, it just popped in. Based on Eduardo's work, I'm wondering about how well behaved the voxel grids are in terms of convergence. There you go, we're unmuting you. Should come up in a sec.
Thank you. Well, I can say that these voxel grids help a lot the convergence of the DDES and WMLES, because now we have like almost an isotropic mesh on the wake, so this helped a lot the convergence. And I would say that it will be the standard for the DDES and WMLES simulations now.
Great.
An interesting one here, since we've done lots of adjoints and everything is gradient-based optimization, somebody asks if there are any plans to integrate different optimization methods that do not require gradients.
Yeah, I think since we have a few packages available that are kind of generic off-the-shelf open source things, so we have the SciPy optimizers available. I'd have to go check if there are any that are not gradient-based available, but I see no reason. So I mean, in some of our old Python wrapper layer, we were able to do this, to launch optimizations and sweeps of jobs without being tied to a gradient-based optimization. So it's something we can look at in the Python scripts, but I see no reason. We're also working on connecting new optimizers, sets of optimizers, and I think we're looking at a version of PyOpt. I think PyOpt sparse, I think it's called, to integrate. Yeah, and I'm sure there's something for gradient free in there.
I can add a little bit more, and they can get in touch with us if they wanted to follow up on the conversation. But indeed, the PyOpt sparse package in Python allows you to have access to a number of different optimizers, from the ones that are available inside of SciPy gradient-based to things like we use at Stanford as an opt, for example, et cetera, but also to a number of different genetic algorithms and different sampling methods, trust-based, surrogate model-based type of models, et cetera, et cetera. So the idea is, I think, as we continue along, to perfect the Python interface such that individual simulations can be launched, and then they can be connected to any type of optimizer that does not need to be gradient-based.
Okay, great. Thanks, Juan. Let's keep moving through questions. There are a lot here to get through. So there's a question on topology optimization work, just to describe what topology optimization work has been carried out in SU2, for instance, within FSI. So I think, Pedro, if you're still there, you can probably share your work in that area. Maybe we lost Pedro.
Sorry, I think he was muted. Pedro, you're unmuted now if you're available.
I heard the question, yeah.
Okay,
so what
great.
can we do? We have the same methodology basically, and it can be used together with FSI, with anything you can imagine. It's completely integrated with all other capabilities of the code. So it's not integrated with the optimization framework. You kind of need to set up your own optimization, because it has different input files for the variables and so on. But yeah, we have a paper on that in the SMO journal recently. It's called I forgot. Just a second. It's called
While you're looking for it, maybe we can move to another question.
It's called aerodynamic driven topology optimization of compliant airfoils on the SMO journal, and that describes what we can do with SU2 at the moment.
Great, thanks, Pedro. Another person asks about the future of transition prediction in SU2. So for a long time, we've had parts of the Langtree mentor model available, but was still kind of in final debugging mode. Since then, there's been at least one other one equation transition model that was put into the code, and I think that folks at Twente are also looking at updating the Langtree mentor model. But I don't know the latest status on that. We were waiting for some of the scalar equation work to be complete, so might have to come back to that in the future. But there is, in short, there's some development work going on there in that area.
So Edwin, maybe Edwin van der Weide, I don't know if he is available, but I unmuted him in case he wants to comment on that at all.
Can you hear me, guys?
Yep.
Yeah.
Okay.
Hey,
yeah, I think Tom put it nicely. We started working on the transition model, but then there were so many changes that we put it on hold, and then Tom actually advised us to wait until the general scalar transport equation framework was there. So basically it has been put on hold for a while. But I thought that I saw in the agenda that somebody else is going to talk about this, right? On Thursday or Friday or something, if I'm not mistaken.
Yeah, that's correct. So there's at least one other group who's kind of picked up some of the scalar equation work, and we'll show some results here. And also, if he's available, Daniel's effort that he showed during this talk today is built on it's built on the same scalar framework. So all of those things are kind of converging, and we hope to release that relatively soon. There's a pull request open that's paused, and I think, Daniel, maybe if you could say a word. I think we were intending, or you were intending to do a pull request before too long, right? So let me try to unmute you if you're there.
Yes, I'm here. Can you hear me?
Mm-hmm. Sounds
okay,
good.
Yep. Yeah, so the flamelet branch is based on the scalar branch, and the pull request for the scalar branch was filed first. But since we have continued working in the flamelet branch, we are going to file a pull request for the flamelet branch, and then it will basically overtake the scalar branch. And we are going to do this probably during the next 2 months, I guess. So we might separate out some of the features. So today I talked about this automatic remeshing, for example. We already have a small feature for geometrical constraints, and I wonder if we should maybe split off those features and have several pull requests and not everything in the claimant branch. But during the next 2 months, I would say this will become online. Does this answer your question?
Great, thanks, Daniel.
On just a logistics one, people are asking if these presentations will be available on the internet for going through them again, because some of them will like to rewatch the presentations for better understanding. So maybe Tim can comment on that if he's able to, or if not, let me unmute him. Tim, is your audio working? Or we're going through them again, because some of them will like to rewatch the presentations for better understanding. Okay, I'm muting Tim because his audio is not working. So just to answer that question, we are putting all the presentations on the SU2 Foundation agenda page. So you should be able to get the PDFs or the PowerPoints, whatever they are, for each one of the presentations. But we're also recording the entire session for each of the 3 days. And as you may have seen also, it was streamed live. So the entire video of all the presentations will be available shortly, and we'll communicate to everyone where that is. The live stream through YouTube, I think, also comes online very quickly. So we'll post something, but yes, in short, everything will be available for people to review.
Yeah, everything's available. And if I could add, don't forget there's extra content that wasn't even covered during the meeting. So just to reiterate that, there are more slides and several videos, 5 or more videos that people have uploaded their full-length presentations that are also on the page. So check that out. Okay. So I think this is more of an editorial comment from somebody. They say that mesh deformation based on linear elasticity requires a more robust preconditioner. So I don't know if anybody on the developer side here has an opinion on that wants to chime in.
Well, we have a direct sparse solver that you can use.
Have you tried that with the linear elasticity deformation routines, Pedro?
Yes, it just uses a lot of memory as any direct sparse solver, but it solves the problem.
With the limitations of the linear elasticity, obviously, but yes.
Yeah, exactly.
I would say, Pedro, is if the mesh deformation scheme is relatively simple code, so I think we should invite people in the community to just jump on and develop better preconditioners if that's possible.
That'd be great, actually. With my experience with for sure, we have a lot of room for improvement there. So we did some work a few months ago to make that more accessible for anyone to contribute. So that will be very good.
Yeah, that's maybe just a good comment to make in general. All of these open questions, they're worked on by people like us and people out there that are listening. We need all the help we can get. So if you're interested in a topic, just either post on GitHub that you want to work on it, or start working on it, make a fork, open a draft pull request, contact us on Slack. We need all the help we can get. So there have been multiple comments about, can I collaborate? How do I get started? So yes, please. The answer is always yes. Okay, there's another comment about meshing. They say that there's no inherent mesh generation utility or functionality. If that's true, which yes, that is true, do you plan to include one in the future? And so I think we touched on this a little bit. So far, we've always sort of shied away from doing our own meshing work, just because that the folks in the community up to this point, we're not meshing experts, although we collaborate with a bunch. So I don't think it's on the roadmap now, but that's always open for discussion. We, of course, collaborate a lot with the folks at Indria, for instance. We know people are using open source tools. If any of the other developers want to make a comment about meshing or meshing tools, feel free.
I just add on that the way the whole SU2 community got formed, most people were from the physics and the solver side, and fewer from the meshing side. So naturally, it's evolved into importing meshes from other packages. But I think this is an integral part, and again, we welcome collaboration and thoughts from people who are in the meshing side to help out. So a nice transition in meshing. There's a question that at least I resonate with a little bit, is this idea that multi-grid approaches would be nice, they say. And maybe Tom, you can comment on the capabilities we have in multi-grid, but also maybe throw out there something for people to think about algebraic multi-grid technique.
Yeah, I think that would be interesting. I toyed around with the idea of putting in some form of an algebraic multi-grid a while ago, but never did it. So right now we have what's available is a geometric FAS multi-grid, kind of a classic geometric multi-grid for unstructured codes based on agglomeration, which has served us fairly well. It has a few hiccups for viscous problems with highly stretched meshes that are well known. That's just life if you start stretching the mesh with multi-grid. But I know at least one person in the past has coupled the code to PETSI, for instance, that has a bunch of these things available, preconditioners and solvers themselves. Other than that, I don't have any other comment personally from linking things, but maybe if any of the others have tried algebraic multigrid, talk about it.
I have to say, Tom, I've been personally interested in trying algebraic multigrid. We collaborated a lot with people at Livermore National Laboratories here, and there's a group called CASC that produces the Hyprit, I guess, blocks, and in there has an algebraic multigrid capability, which in theory has undergone lots of improvements for systems of equations over the last few years, but we have just not had the bandwidth to try it. But it would be a great thing to try with somebody in the community.
Yeah, great. So there's a comment, Alberto, if you'd like to join, we can make you, we could promote you, but you've left a comment saying that concerning mesh deformation, Tommaso tomorrow will present RBF methods. So that's something to look forward to. Oh, we'll just, looks like we're having audio, so we'll just leave it muted.
Something seems to be wrong with the audio for Alberto. Maybe we can all.
Yeah, sorry, Alberto.
And then mute him. Let's try one more time, Alberto. Okay, then maybe we'll just say that Tommaso Belosta is presenting tomorrow this radial basis function methodology. I think it's tomorrow, right? At the end of tomorrow, a radial basis function methodology for mesh deformation, which they're using for very complex, shapes of airfoils under icing conditions, and that seems to be working quite robustly. So I'm sure Alberto and Tommaso will be more than happy to share any of the developments that they made with you guys.
Yeah, and that reminds me, earlier in the session, there was a question asking about whether some of the work that Akshay was doing on roughness could be applied for icing. So I would say for the person who asked that question is stay tuned tomorrow to Tommaso's talk also for that. Okay, maybe one more question that we skipped over until now. This is always a hot topic for the numerics people here can chime in. So comparing the limiters inside of SU2s, my observation is many times the Van Albada edge limiter is doing better than the Venkatakrishnan and the Venkatakrishnan limiters, which is interesting, they say. So any plans for improvements in this direction? Maybe not. They understand that there aren't too many options in the literature. So anybody have opinions on this? Maybe Eduardo's virtually raising his hand. Why don't we unmute you?
Go ahead, Eduardo.
Okay, I think one thing that we can do to improve is use what people call in the literature is a secondary limiter. and there is some works on this topic, and I think we can have a look on that.
Yeah, this is related to the post limiter work from Catarina, right? If I recall.
Exactly.
Yeah, okay. Yeah, I think what we have in there are sort of the classic textbook or publication versions of these things, and we could do a little better to sort of customize them and handle dirty cells and these types of things. So yeah, that's a good point.
Exactly.
Okay, well, I think we're about out of time. I think we covered almost all the questions. If not, what we're going to do is export them, and we'll keep a copy. So if we didn't get to something, we'll do our best to get back to people. And another comment is that during the talks, we have forwarded your questions along to the speakers. Most of them, I think, have gotten back. If not, we also are copying the questions, and we'll personally sort of pass them on to the speakers so they can contact you and respond to those questions. So. Well, with that, I think we're right at 10:30. We said we would adjourn today. So I want to thank everybody again for coming. Thank all the speakers. This is a really great first day. And we hope you'll all be back tomorrow at 7 a.m. again, Pacific time. We'll start bright and early again. We hope you all enjoy the rest of the conference. So thanks again.
Thank you.
Thank you, Tom. Thank you all.
Thank you. Bye-bye.